Welcome to the day 0 of the LLM Mastery course. In this video, we are going to see about the prerequisites which you should know before going into the course in deep. The prerequisites itself are a lot to cover, so I made it as 3 parts: beginner, intermediate, and advanced. In this video, we are going to see about the beginner prerequisites. Let's start with the beginner prerequisites. What is natural language processing? Natural language processing is a subfield to artificial intelligence and computer science, which focuses mainly between the interaction of computers and human who use their natural languages. But what is the goal of NLP? It is to enable machines to understand, interpret, and generate meaningful content to the humans. In essence, it is just a subfield, which will be covering computer science, artificial intelligence, and human language, because it is trying to bridge the gap between human communication and computer understanding, which is by allowing machines to read, hear, and make sense of what human is speaking by training it on vast amounts of human language data. Now, what are the key components of NLP? First, syntax. As we all speak syntax in programming languages, even natural language has its own syntax. Syntax is often defined or referred to as the rules that governs the structure of the sentence. For example, the verb should come second, noun should come first, something like that. In NLP, syntactical analysis, or parsing as they say, it is used to assess whether a sentence conforms to the grammatical rules. There are grammatical rules to be followed when you are making a sentence, and syntactical analysis helps you to assess if that is correct or wrong. Semantics. As the name suggests, it involves understanding the meaning of words and sentences. Semantic analysis allows the machine to grasp the content and disambiguate words with multiple meanings. What is meant by that? Let's take an example of bank. So, for example, if I'm saying I went to a bank for getting my loan, which is located at the end of a river bank. Here, I'm using bank at 2 places. One is referring to a financial institution, and another is referring to end of a river. So here, the computer or AI is expected to understand the meaning of the word and sentence, by which it will understand the context and say, okay, the first bank, since I'm saying about loan and getting something out of it, it is going to refer about a financial institution. And since we are saying it is located at a river bank, it will say it is the end of a river or something like that. Okay. So semantics is very important. Third one is morphology. So what is morphology? Morphology is the study of structure of the words, such as root, prefixes, and suffixes. For example, advantage would become disadvantage, and play will be like playful, something like that, which will be prefix and suffix. And here, the root word will be play. Play is becoming playing, playful, playfulness, whatever you want, adjectives or verbs, but the root word is play, right? Morphological analysis breaks down the word to their constituent part to derive meaning. You might say about playfulness or whatever it is, but it will first understand that, okay, it is something related to play. Pragmatics. Pragmatics deals with how language is used in practice and how it influences meaning. It is mostly about machines understanding the indirect language. So, for example, we say I am on cloud 9 that I'm launching this course. So it should understand that, okay, I'm very happy that I'm launching this course, right? So that comes under pragmatics. So mostly pragmatics is about the machine understanding the indirect language, especially with idioms and phrases. Next, phonology and speech. For spoken language processing, because in NLP it is not gonna be just about text, it is also gonna be about audio or sound. So the sound of the speech will also relate, how the language is spoken. For example, if I'm shouting a lot, it means I'm trying to convey angry emotion out of it, right? So those are very important when you are processing the audio, because there are use cases like audio emotion analysis. Now that is about the key components of NLP. Next, let's see about the common tasks in NLP. So you can say it as tasks or applications of natural language processing. And here you can see there are a lot of things: smart assistant, document analysis, predictive text, chatbots, and so on and so forth, language translation, automatic summarization. But these are, an end application. But at a task level, how we define that? Text classification. There is a text data, and we'll be assigning a predefined category to that text data. For example, if the use case is spam detection, ham or spam, if the email is something, good, or if it is like, spam, something like that is spam detection. And with sentiment analysis, it depends. People try to do it either for positive, negative, or sometimes people also add it as positive, negative, neutral. But the idea is that it is to express the sentiment or identify the sentiment which is expressed in the sentence. All right. So that is about text classification. And here, if you see, we are having a set of, categories, and we are trying to assign those categories. So the perfect definition of text classification would be assigning predefined categories to text data. Because even if you see the product reviews, right, I could have even classified it as type of product, right? So the TV is not working well, I would have classified it as electronics. If my use case was to classify the category or product category, right? So we are assigning predefined categories, and that would be the explanation about text classification. So what is named entity recognition? As the name suggests, it is to recognize the named entities. So what are named entities? People, organization, dates, locations. Usually your nouns will be named entities, right? So recognizing those will be named entity recognition. So if I say I am making a course on generative AI, so I will be a named entity because it is saying about some person. And you might now wonder, okay, Vasanth, you said noun. No, here I'm saying about pronoun also. Okay. Let's start with machine translation next. A machine translating text from one language to another is machine translation. Also, you can put it as one form to another. And why is that? I'll explain now. Popular applications like Google Translate have multiple language support, which is known as multilingual support in their AI systems. And you're also able to see, Google Translate is there. That is language translation. But when we put it as machine translation, there is some another thing we need to see. If you want to convert a text to code, it is also one language to another. Okay. So that is why it is said as one language to another. But you should understand that code is also a language. So if I'm saying text to code, it is about machine translation itself, where the machine is expected to translate a text into a code. Hope you got that. Now let's move on to part of speech tagging. What is part of speech tagging? Labeling words in sentence as noun, verbs, pronouns, adjectives, and so on and so forth, so that it will understand the grammatical role of each of those words. So if I'm saying I'm recording prerequisites for my course, okay, it will say I, it is noun or pronoun here. Am is verb, recording will be another verb, where am will be an auxiliary verb and recording will be a primary verb. Prerequisites, again, it is going to be another noun, right? So it will understand, what is the grammatical role of each of these words in a sentence. So we usually classify it as text classification, but often sentiment analysis by itself is considered as a task, because the amount at which every companies try to use sentiment analysis is pretty huge. So that also is provided as a separate task here where we'll try to identify the sentiment. All right. And then we have question answering. As the name suggests, building systems where once I provide a query, the machine is expected to provide a correct answer based on a body of knowledge. Either it knows by itself or we provide it or something like that. Okay. So this is the foundation of systems like IBM Watson or ChatGPT, whatever you see. It is all about, or it is down to question answering, speech recognition and generation. So it is formally known as speech to text and text to speech. Okay, when you convert a speech to text, it is going to be your speech recognition, and when you convert a text to speech, it is going to be speech generation. Next, we have text summarization, one of a very complex use cases which you can do with AI, because it is about automatically generating a shorter version of a long context while you retain the essential meaning. Underline this phrase while retaining the essential meaning, because when you're going to summarize, it is about you understanding the whole context and then rewriting it in your own words. So that is why summarization is a pretty complex task in its own way. Co-reference resolution, identifying when two or more expressions in a text refer to a same entity. So what is this all about? So let's take this itself. Let's consider I am John. Okay, John is recording prerequisites for his course, and he is now moving on to the next topic, techniques of NLP. Here he refers to John, right? So they are referring to the same entity. Language modeling. Language modeling is a task even which is used in pre-training of LLMs, which we'll see in detail later, where the idea is that the machine is expected to predict the next word, which is essential for tasks like autocomplete, text generation, and so on and so forth. And when you say about text generation, it will cover everything. Any kind of text which is generated is text generation. So in a way, or in machine's own way, we can say even text summarization is text generation. Now let's see about some of the techniques in NLP. The NLP has evolved significantly or drastically, so to say, driven by the advancements in machine learning and deep learning. And here are some of the most prominent techniques or the models used in NLP nowadays. First is rule-based methods. You might wonder, there are LLMs right now. There is a lot of big models, even if not for LLMs, who uses rule-based methods. You see, when you use transformers or LLMs or even neural networks, there is a sense of, unpredictability or uncertainty that your model might go wrong, right? But with rule-based methods, since it is handcrafted, right? Please note the word handcrafted. You have crafted the rules to process the language by yourself, so it can never go wrong. Yes. The issue is that there is limited scalability and adaptability. Unless and until you write a rule for every single change in your use case, you won't be able to go for rule-based methods. But that is something you should always have in your mind, that if I can solve it with rule-based methods, I'll go for rule-based methods, right? So that is why even in text processing, we'll write rules, which is most probably regex rules, to process the data rather than giving it to LLM, right? The reason is not that it is not just computationally intensive, it is also on the fact that you can't trust an LLM to generate an output and making that as an output to train your own model with that as an input, right? So that is your rule-based methods. Now, the next one is machine learning. Machine learning is the base for whatever we see nowadays, and even that has been used for a lot of use cases for some time before, and that is known as modern NLP. That is where modern NLP started. So for that, It will use supervised and unsupervised learning techniques, and the algorithms like naive Bayes, support vector machines, decision trees, and so on and so forth has been used for NLP tasks like classification and clustering. Now, if you might wonder what machine learning models for NLP doesn't seem, impressive, so to say. I'll show you at the end of this prerequisite section where we'll be training a naive Bayes model for text classification or sentiment analysis to be precise, and we'll see how much accuracy it gets. Right? Now, coming on to deep learning. Neural networks, especially RNNs and LSTMs, which is a variant of RNN, along with that there is CNNs as well, is used widely in NLP to handle tasks that involve sequential data, which is like text. Like I said, especially LSTM. LSTM has a capability to capture long-range dependencies in text. And LSTM is abbreviated as long short-term memory, right? So we'll be seeing about LSTM, RNN and all later, but you should know that in deep learning, there are neural network like RNN, LSTM and all, which is used for use cases with text. With RNN and LSTM, it is not just that you can do with use cases like sentiment analysis. Anything which will involve sequence can be used with long short-term memory networks. So even it can be your stock price prediction, based on the history of data. I want to predict the next day data or next day close price. That can be done with the help of deep learning. Coming on to the most revolutionary architecture after CNN, in my opinion, which is transformers. The introduction of transformers basically revolutionized NLP, and unlike RNN, transformers can process words in parallel, and that will help it to capture better context. There are models like BERT, GPT, and TF-IDF, which are based on this architecture as its core and have achieved state-of-the-art results in many NLP tasks then, right? But why did I stress on the word then? It is because of this thing which has come recently, which is pre-trained language models. You see, language models are also transformers, but the way it has been pre-trained, the large-scale pre-training models have basically changed the NLP landscape. These models are trained on vast amount of data and then are fine-tuned with specific tasks. There is BERT, GPT-3, MBART, which are all like, let's say the parent models of all the models we are having right now. And these models are the ones which have made NLP more accessible for applications like chatbots, translation, and even creative writing. Creative writing is a very complex process, and transformers has paved way for that. Now, we are seeing about the introductions to NLP, but it is very important that we understand the challenges which are there in NLP, and that is what we are going to see now. Though there are numerous advancements which are there in the field of NLP right now, still there are some challenges. First is ambiguity. Language is inherently ambiguous. So whenever a language is there, it is always going to be ambiguous, or you can say, we say like, double meaning or triple meaning words, right? For example, the word I said as bank. So to understand that, it is very important the model understand the context, tone, cultural factors, and so on and so forth. Yes, nowadays models are better on that, but still it is a very big challenge. Next one would be context understanding. While transformers are improved context capture, still maintaining long-term context in lengthy conversation or documents is still a challenge. Right now, if you see 4096 is something very common as a context length, but after that, the model can't handle, right? So that is still a problem, okay? And then multilinguality. Developing NLMs or NLP systems, basically, that works seamlessly across multiple languages is very complex because the grammar is different, syntax is different, cultural references is different, and more importantly, the data which is available for some low resource language are very less, so that you can't ever match, we can say it is highly unlikely because we are all data scientists and we can speak only in probabilities. Never we can say that it is impossible. So it is highly unlikely that you can train a model which will work close to same for any languages in the world. So universal models are very difficult to create. Bias present in language models. Since NLP models are trained on large data sets which are scraped from internet, they inherit and learn whatever bias is present in that data as well. Yes, there are efforts made to make sure that these models are equitable, but still there will be bias, right? For me, the most important challenge, and still people are trying to solve this, at least these four, we have made a lot of advancements in it. Previously we had only 500, now we are moving towards 4096 context length at ease. Ambiguity is something now LLMs are able to understand. Multilinguality, yes, like I said, it is highly unlikely that you can create a model which will work for every language as similar as it works for English, but still, it is not like how it was before. Bias, yes, people are making a lot of processing steps and trying to avert that issue. But the most important problem, that is why I have kept it as the fifth issue, which is common sense reasoning. Reasoning is something what differentiates human from any other species, and it will also include AI. If I consider AI as a species, the only thing which humans have over AI is reasoning, because AI is more efficient than human, but it will always struggle a lot with common sense reasoning. And we can update our knowledge, and unless and until an AI can update itself, it is not gonna get the real world knowledge at any time it wants that human can do, right? And also reasoning, like I said, reasoning is something which is very challenging with NLP field right now. So we have seen about a lot of things. Now let's see about the applications of NLP, how it is used in various industries. First things would be search engines. NLP is the core of search algorithms. If you all remember, in the techniques of NLP section, I have said about rule-based methods, right? Search engines previously were rule-based, right? And still, it is mostly rule-based, okay? Even if you go for Google search, the search results are mathematical rules, right? There is an AI assistant which is there, that is fine, but the search engine results which Google provides, it is only because of rules, okay? So NLP is there at the core of search algorithms, helping understand and rank relevant user queries. Results. Virtual assistants like Amazon Alexa, Google's Assistant, Apple's Siri, all use NLP to understand spoken commands and respond appropriately. Customer service. Nowadays, chatbots are used in customer service, and those virtual assistants use NLP to understand the inquiries and provide solutions automatically. If they can provide, they'll provide themselves, or else connect it to a technical person so that they can help solve the problem. And there is healthcare, where NLP helps in medical data processing, summarizing patient records, and so on and so forth. In social media, there is sentiment analysis, trend detection, so that you can capture the trend and probably make it big. So these can be done with the help of NLP to interpret user interactions. And one of the most important applications of NLP domain is legal and finance. To process legal documents, financial reports, or automate contract analysis, NLP has been used very widely in legal and finance. So as a summary, you can say that natural language processing is a dynamic and rapidly evolving field that gives ability for machines to understand, interpret, and generate human language. From rule-based systems, it has moved to transformers, and we have come a long way right now with LLMs. But however, still, like I said, there are challenges and it has been used in various fields due to its advancements. Next, we are going to see about the NLP pipeline. The NLP pipeline consists of several stages, which will convert a raw text into structured data which is suitable for model input. And then we'll train the model and then so on and so forth, right? So it will start with text input or data collection, and then we'll process those data, we'll represent those data. And what is that? It is the stage where you create embeddings. And then you'll select some features if you are doing that. It is not something which you commonly do right now. And then you have your model selection and training, where you'll select what model you want. Like I said, there are numerous techniques in NLP. It is upon you, like what you choose for your model. And then you have model deployment, and then we'll evaluate at real time and then improve it. So this is how an NLP pipeline works. But let's see about each of those component at an overview with answering the questions what, when, how, why. In this course, I would have emphasized more on what, when, how, why, because that gives you crux about any component and it will allow you to apply your knowledge better. So let's start with what on data collection. What is data collection? It is a process of gathering raw text from various data sources. So when you'll do that at the first part, where you'll collect the data for training according to your use case, obviously. And then how will you do that? There is web scraping APIs, there are open source databases or closed source databases, and generally we can say it as databases, or user generated content or AI generated content nowadays, right? So these are the ways you can collect data for training your model. And why you should do that? It is very necessary because that is gonna be your model input for its training. Data processing. It will involve techniques like cleaning, tokenization, vector representation, and so on and so forth. All will come under data processing. So what is data processing? Data processing is a stage where you prepare the raw text data for analysis. And when you will do that, it is before you build the model, where you have ensured that the data is good for the model to be trained on. How will you do that? It is through the various text pre-processing methods, which I will discuss in the next section. And then why you need to do that? It is to ensure that you have consistency in your text and the data quality is improved, because you're collecting it from internet and so on and so forth. There will be bias for you to remove. There will be a lot of mistakes. There will be missing data. You need to handle all of those. It will be very unstructured. To handle all of those, you need to do data processing. Next, we have model building section. And what you will do in model building? We'll be creating and training NLP models on the processed data. So once you process the data, you'll create and train your NLP models. So this creation of models and training those models is the model building phase all about. When you'll do that, like I said, once your data is created, the model will also be created along with the training paradigm, because the training pipeline to be written is very important, because just model is not going to train by itself, right? You need to create your own training paradigm. That is a very important step, which will be added in model building by default. So why you need to do that? Obviously, you need to develop models which has the capability to understand and generate languages. And how will you do that? You'll use the techniques of NLP which we discussed before. It can be rule based, it can be machine learning algorithms, deep learning architectures, pre-trained language models, or so on and so forth. Inference or testing. So what you will do here? You have trained your model. Now you need to make predictions or generate output, whatever it is. So that is what is inference all about. When you will do that, as like in the definition itself, once you train the model, this model is used to get new results on new data. Or you can put it as mostly unseen data, because we can't say 100% sure that this data was not there in pre-training or fine tuning. If you are creating a small model by yourself, you can say with some surety, but with LLMs, you are using internet data. We can't say like, this data is not something which has seen. So I've just put it as new data. How will you do that? You'll use like new data will be fed into the model and the trained model will interpret and provide the output accordingly. And why you need to do that? Then only you'll complete your use case. That is like the basic thing. And also while evaluation, basically you'll need to infer your model. So that is why. And deployment. Deployment is a stage which is about making the NLP model available for real world use cases. And it is done after rigorous testing and inferencing on some real world users. Inferencing with some real world users, or we say it as beta testing, basically, right? After that, only we'll be doing deployment. And how we'll do that? There is APIs where you can say like, this is my model hosted, and there is cloud services, which is almost similar as APIs. And then there is on-premises infrastructure where there are some companies who want to keep their model to themselves, and then like, they'll try to use on-premise infrastructure. Why you need to do that? Basically to integrate the NLP capabilities to your products and services. Now you have an idea about all of these specific components at an overview level. We'll go in deep at each of these components at some point of time in the course, right? But it is very important that you address this specific component, which is data processing, because this is not something which we spend a lot of time on, but it is a very most important component. So let's go on with data pre-processing next. Data pre-processing or text processing. Basically here the data is text, so text processing can be said as data pre-processing. So this is a crucial step which is happening after data collection and before model building. It is essential for cleaning and preparing raw text data so that the data quality will be improved and will be consistent for model to be trained on. So what are the steps? Usually, like, in old times, this is how it will be happening. And why I'm saying at old times, with LLMs, everything has eased up a bit because LLMs have tremendous capability to understand even, some amount of unstructured data or unclean data, so to say. But even if you give unclean data or clean data, both, right? Clean data will give the better performance. So it is always good to clean up your data a bit. But the extent at which that happens previously with normal neural networks, that won't be required nowadays. So this is how the text processing pipeline basically goes. You'll remove the text, you'll do stemming or lemmatization, you'll tag some POS, and based on that, you will clean your data, and then tokenization will happen. This is how the pipeline works basically, but we are not going to go like that. Okay? We are going to see how basically in real world text processing happens. Okay? We'll go for the methods and we'll answer the question as usual: what, when, why, how. Text normalization. So as you can see here, it was he visited in London, he visited London, he visited London. All our caps here, caps in small. This is probably the most worst data, so to speak. And once you normalize your text, it is expected to have this kind of an output. Okay. Converting the text to a standard format is text normalization. Example is lowercase. You can have anything. For example, making it as everything as capital could be your standard format, and that is again text normalization, right? So when you'll do that at the beginning of text processing, then why you'll do that? It is to basically reduce the variability in the text. Because see, if you have everything as small letters or everything as capital letter, there is some kind of a consistency, right? Where it is not something which we see here or here or here or anywhere. Like, if I see all of these in my data pipeline, let's say all of these 4 sentences are in my data set. For each, I would require to write different rules, right? So that would not be the case once you normalize your text. So that is why it is done at the beginning of text processing. And how will you do that? Basically, you can use string methods or custom functions. So here you can see this is a sample text. And if I call text.loader, it is going to be, this is a sample text. But if I call text.upper, it is going to be an uppercase. Okay. So it is upon your choice. If you want to make it uppercase, it is uppercase. If it is want to be a lowercase, you can keep it as lowercase. The usual convention is to keep it as lowercase. That's all. Regex, one of the most underrated aspects which is there in NLP, but has a tremendous potential. So this is a regex expression, or by regex by itself, because regex is abbreviated as regular expressions. So here capital A to Z says that it is character from A to Z as caps and A to Z again smalls. So square bracket considering this character range. Okay. Here we are seeing 2 with the bracket, right? So it means that exactly 2 occurrences of any character from the preceding pattern, which means there can be 2 characters. Okay. It can be capital, small, capital, small, small, capital, but there should be only 2 characters. And then followed by that, there should be digits, which is from 0 to 9. That is what /d says. And there should be only 3 occurrences of those. So basically, these are the format of Harvard courses. If you have seen it, is CS 229, CS 231, so on and so forth. Okay. So for that, you will write a regex like this if you want to process this specific sentence. Okay. So what is that? It is a pattern-based text cleaning and extraction procedure. And when you'll do that, it is in early stages of text processing pipeline, but it is mostly done after or with normalization at some times. Why you will do that? Basically to remove or modify specific patterns in text. If you don't want some specific patterns in text, if you want to remove those, then you will do that. For example, URLs or special characters or so on and so forth. How will you do that? You'll use RE module in Python, which is default, to perform regex. I'll go in detail about regex, but here is a sample. Okay. Right now, my thing is that I don't want the link there. And if I call this, it will just remove that. And how will this happen? We'll see in detail in the regex section. Okay. Next is probably one of the most important aspects in text processing, which is tokenization. Tokenization is a process of breaking a text into smaller units, which is known as token, which can be usually subwords, words, or even characters. When you will do that, once you're very sure that the text is good or normalized. Why you'll do that? It is to prepare the text for further analysis or even to provide the data to the model. How you can do that? There are lots of ways. There is NLTK, there is Spacey, custom functions can be written, or even you can use Hugging Face tokenizers. Okay. So we'll be again seeing about tokenization as a detailed section later in the course, but just to say, here you can see word token. What it will do is it will tokenize each word separately. So it will be NLP is fascinating. All will be separate. Okay. So you can see NLP is fascinating has come as separate. Now, here you have stop words removal. This is not something which is done nowadays. All right. Because when you remove stop words, it is basically collapsing the structure, though it doesn't carry a significant meaning, but it was done before. Okay. The process is, like I said, eliminating common words which doesn't carry any meaning. So usually after tokenization, if there is a word which doesn't have any meaning, those will be removed. Basically your stop words, okay, or your auxiliary verbs, so to speak, and like your adjectives can be used, but this and these kind of words won't be used. Okay, this is to reduce the text and noise in the text and focus more on the meaningful words. And how it is done? What we'll do is we'll have a set of stop words by ourselves, and then we'll make sure that these words are not there. Okay. Here are some of the common stop words. I, the, in, off, for, at, to, on, with, from. These all carry very less meaning. At least from and to have some meaning, but not everything has some meaning to it. So basically these are stop words. So in NLTK itself, there is stop words. And if I do, this is a sentence, sample sentence with stop words. And when I tokenize it, it will be, this is a sample sentence, everything will be words. And here we are seeing if those are not in stop words. So this is with all of these are in stop words. So those are eliminated and others are printed here. So next we have stemming and lemmatization. So stemming and lemmatization both are about reducing the words to another form, where stemming focuses on root form, but lemmatization focuses on lemma, which is the dictionary form. When this will happen? After stop words removal. Why? Again, to reduce vocabulary size and simplify the text. So because each token or each word will be a separate entity in your vocabulary, and with increase in vocabulary, the model to normalize itself across the vocabulary, it will have a lot of requirement for training, and also for while inference, the time will also take a lot. Okay, how will you do that? You can use rule-based algorithms like photostemmer in stemming, and for lemmatization, you can use part of speech information and all, which is usually done with the help of word-net lemmatizer. Okay, so first I'll show you here. It is run, ran. Okay, and here it is good, run and eat, or better running and eat. Okay, so it will not change a lot of things. Okay, it will capture those information whenever it is required. But if I did, like, for example, betterness, right, it will still give betterness. Okay, so that is why people usually don't prefer lemmatization, because betterness is something would have been there in dictionary. Okay, if there is a word in dictionary, it won't do that. Okay, that is about lemmatization. So if you want to do it in your root word, it is better to go with stemming. But if you want to make sure that the word captures some meaning, because that is not something which is usually the case with stemming, you can go for lemmatization. Now, like I said, we are going to see about regex text processing in detail, because that is something which is very important, and it plays a crucial role in text processing to standardize and clean the text. So what is regex? So it is a sequence of characters which is used to define a search pattern, and it is used to do pattern matching and text manipulation basically. When you will do that, it will be done during the initial text cleaning phases, often right after or combined with normalization. Throughout the text processing pipeline, for specific cleaning tasks, you can use regex, because even in post processing you might require. Okay, why you will do that? It is to again efficiently remove or modify specific patterns in the text. It will standardize more, you can extract information, and so on and so forth. How will you do that? Using the RE module, but we are going to see in detail those right now. Okay, common methods are re.sub, which will substitute the pattern with a replacement text. Find all, which will find the occurrences, all the occurrences based on the pattern we gave. And re.search, what it will do is it will find the first occurrence. Okay, so here are some of the common regex operations. First is removing special characters. So if I say hello, exclamatory mark, how are you, question mark, I, quotes, I'm doing great, hashtag happy. So it will remove all of those special characters. And why is that? Here we are making sub. Okay, re.sub, which is substitute. And here the bracket is open, right? So here A to Z clashes. Okay, so basically if it is not a character, I'll remove those. That is what this thing is saying about, like, anything which is not a character that will match this pattern, and I'm going to replace those with empty string. Okay, so that is why hello, how are you doing, I'm good, doing great, happy is coming like this. Removing extra white space, again slash is space. Okay, anything which is not a character or a space will be replaced by text. Now you might wonder, will that happen for numbers also? Yes, it will happen. If I had a number in here, it will be removed as well. So that will be the case for removing extra white spaces as well. If I have, numerous white spaces, I'll replace it with one space. Okay, here you can see there is 3 to 4 space between each, and those are provided as this has extra spaces. This is how you'll remove trailing white spaces, so to say, as a technical name. If you want to extract the email, right? So email passing is something which is done a lot of times, and this is how you can do that. Okay, find all occurrences of email, where the structure will be A to Z numbers, or it can also include underscore and so on and so forth. Okay. And here are some patterns as well. It is a detailed pattern. We can go in detail at some point of time, but this is how you will extract the emails. So how will you remove HTML tags? We all know that there is a characteristic for HTML tag. There will be an open bracket, there will be a close bracket, and then there will be some values inside that. Okay. So we are saying anything which matches this pattern will be replaced by empty text. So that is why it has become this is bold text. Standardizing phone numbers. So here, if it is this digits or this kind of digits, what we'll do is we'll make sure everything is just empty string. Anything other than digits will be empty string. Okay. But like I said, regex can be used anywhere. You can use it while tokenization. You can clean it and then use for stop words removal. Okay. Everywhere regex can be used, and that is why regex is a very important component in text processing. Next, we'll see about another section, which is vector representation, text representation, or commonly known as embedding. We all know that computers knows only numbers, but text is not number, right? We all know that it is zeros and ones, but even converting number to 0 and 1 are easier, right? So embeddings are what is the in-between phase between text and those zeros and ones. Okay. Embeddings are formally defined as dense vector representations of words or phrases that capture semantic meaning. Okay. And significance of embeddings is that it will capture semantic relationship between words. It will reduce the dimensionality of the text data. It will improve the performance of many NLP tasks. Okay. So that is about embeddings, so to say. It is just a way that you will represent your data, which is text, which can be words or phrases. And this embeddings will capture the semantic relationship between those words. Basically, those will improve your performance. Now let's see in detail about the embedding methods. First, let's see about bag of words. What is bag of words? It is a process of representing a text as a vector based on word counts. When it will be used only with simple tasks like text classification. Why it will be used? It will be used because it will be very easy to implement and understand. How it can be done? Basically, it can be done by creating a vocabulary and counting the word occurrences in each document. Here, let's take this example. The child makes the dog happy. The has appeared twice. Dog has appeared one times. Makes has appeared one times. Child has appeared one time. Happy has occurred one time. Again, the reverse. Here also the will have two. Okay. So if you make numbers of those and then you make a number out of this, that will be a bag of word representation. Okay. Here you can see this is probably the worst method, right? It doesn't capture any meaning. See, if I say like 1, 1, 1, 2, what you'll be even able to understand out of that? There is no difference, right? So that is why, bag of words is not something which is used commonly. And then there was an improvement and came TF-IDF, term frequency, inverse document frequency. Here also it occurs based on words, okay? But it is all about representing the importance of words in a document relative to a collection. So what is this all about? If we see about how you'll understand what, we'll calculate a term frequency, where what it means that is frequency of a word in a document, and inverse document frequency is about the number of documents which contain those words, and we'll make a logarithm out of it, and that will be your inverse document frequency. Because the idea is that if the term is repeated a lot, it means that term is very important. But if you see those filler words, auxiliary verbs, or stop words, so to say, will have the most number of occurrences, right? So to filter those out only, we'll have the inverse document frequency component. Okay. So once you do that, you will have a vector transformation, and here you can see there will be some meaning. Okay, here you can see this is having something, but the is not having anything. Okay, so yeah, so TF-IDF is something which can be used for use cases like text classification and all, and it is a pretty good method for starting. Okay, again, here also it is rule based, and it is not always you can do anything with rules. And then came an approach which is word to vec. Okay, so what is this approach all about? You'll create dense vector representation of words with the help of neural networks. Why you need to do that? You need to provide embeddings that capture context and semantic meaning. When you will do that, when you require, like to capture semantic relationships between words. For simple use cases, those won't be required, but for complex use cases, yes, you need to capture the semantic relationship between the words. How will you do that? You'll train a shallow network on a large text corpora based on the words by using methods like CBOW. Okay, so for example, king and queen will be related, and king will be in the same zone of man, and queen will be the same zone of woman. So to capture this, you need to, make an embedding model. Okay, so if I do this one, here you can see word to vec. The sentences are cat say meow, dog say woof, and here I'm calling a word to vec on these specific sentences. Okay, so it will create a vector for all of those. Instead of cat, if I say meow, still it will create. Okay, so here you can note the number minus 8 e power minus 3 will keep that, and if I keep cat, it is minus 0.007. Okay, but if I say dog, you can see it is e minus 5. Okay, the relationship between the words, cat say meow, dog say woof. So here you can see those are tokens. This inherently shows that once you make your tokens, to represent the relationship between those words or tokens, you will use word to vec. It is not always that you'll have a word to vec model. Like right now, the performance, even I didn't like that. So what you will do then? You'll create your own custom embedding with the help of neural networks like RNN. Okay, when you'll use that, when the pre-trained embeddings doesn't capture the specific nuances of your domain, it is not always that, even like for example financial domain, it won't capture the nuances, so you will create your own embeddings. Why you need to do that? You need to create your embeddings for your specific task, because that is when it is tailor made, which means it will improve your performance. And how you will do that? Basically, you will train a neural network with an embedding layer on your specific dataset, and this is how it will happen. So here I'm having a vocab size and embedding dimension. Vocab size is basically a vocabulary size, the number of tokens which it knows that it is there. An embedding dimension, which is, the vector representation dimension. So for a word, I'm representing it with 512 numbers, 1024 numbers. So that is about your custom embedding dimension. Okay. Basically, this NNN embedding is a dictionary, but it is a learnable dictionary. That's all. Okay. So if I do this right, it will create a custom embedding. And then what it will do is it will give for 5 tokens, it will give 50 tensor of each. Okay. Each tensor will have, or like each number will have a 50 number representation for it. Okay. So it will be 5 cross 50. I haven't trained this, but we can also train that. That is also possible. Okay, and that is how you'll create the embeddings. Okay, now you know how to process your text. Like data collection is very simple, right? You'll go for internet sources and so on and so forth. You'll collect those, you'll process those, you'll represent those with embeddings, right? So now let's go on to the NLP pipeline, which we saw before. We have seen about the data collection small, right? I've said you can collect from somewhere like those and all. Text preprocessing is done. Text representation is done. Feature selection, we won't do that in NLP basically a lot. Now it is about model selection and training. So in methods, already we saw about rule-based methods with Regex. So we'll be starting with NLP with machine learning. That is all about our next section. Now let's see about how you can use machine learning for NLP. So this section is all about integrating NLP techniques with machine learning models. So for all those who don't know about machine learning is just a subset of AI, which is focused on creating systems that can learn from experience and make decisions based on those data. Okay. And why is that required? Previously, it was rule-based. The hierarchy of techniques, if you remember, it is rule-based methods, then it was machine learning. Okay. Those rule-based methods can't adapt themselves and improve themselves, but these models can automatically improve based on their performance through experience. Okay. So these have their own set of rules, but still it can improve upon their experience. So types of ML models. There is supervised learning models, which will learn based on labeled data to predict new outcomes. So it will include use cases like classification and regression, which is spam detection, price prediction, and so on and so forth. Unsupervised learning is a specific type of model where you'll try to find the patterns with no labels. So it will be customer segmentation, dimensionality reduction. Customer segmentation is about clustering things together, which has some similar characteristics. Semi-supervised learning is, as the name suggests, a combination of supervised and unsupervised, where you'll do that when you have small amount of labeled data and large amount of unlabeled data. Okay. And reinforcement learning is something when you have an environment where you can say, like, if you do this, you have, a maximized reward. Reinforcement learning is a kind of semi-supervised learning by itself, where first you will train with labels. Okay. And then what will happen is the model will reward itself. So those rewards are considered to be labels indirectly. Okay. So here are the types. You can see, like I said, reinforcement learning is a type of semi-supervised learning by itself. Okay. But we are not gonna go in detail with all of these types or models. We are going to focus on naive Bayes. Okay. Why naive Bayes? Okay. I think that is very important. See, naive Bayes is something which is very efficient. Okay. Because it is very fast and requires very less training data. It can handle high dimensions. And, like, though it is said as naive, it is very good for text classification actually. Okay. So that is an important reason why we use naive Bayes for text classification. So how will you prepare the data? So let's consider the sentiment analysis. So this is just demo, but we'll see a training separately. So let's say we have 4 reviews here: great product, bad quality, excellent service, terrible experience, positive, negative, positive, negative. Okay. This is our data set. Vocabulary building. So it is about splitting those words, and that will be a vocabulary. Great, product, bad, quality, excellent, service, terrible experience. Okay. That will be a vocabulary building. This is how basically naive Bayes training happens. Okay. So what it will do is it will calculate the prior probabilities. Okay. The probability of being positive out of these 4, it is like equal. Okay. Positive is also 0.5, negative is also 0.5. That is prior probabilities. But what is the likelihood probability? Like, let's say this word is there. What is the likelihood of that word being showing that, like, that is positive? That is about the likelihood probabilities. Okay. This works based on Bayes theorem, which is about conditional probabilities. Okay. The probability of A given B is equal to probability of B given A star probability of A by probability of B. Okay. So given A given B is about occurrence of A and occurrence of B. So this is all about saying, like, for example, probability of great being good is equal to the probability of good, like, the sentence being stated as good given great by the probability into the probability of great occurring by the probability of good. Okay. That is how the formula is with Bayes theorem. When you apply those, these are the values you get for the positive classes, and these are the values you get for negative classes, right? And when you do for text classification, let's say you do it for good product and bad product. Okay. Good product for positive and good product for negative itself. Okay. We'll see about good occurring in positive and product occurring in positive, and good occurring negative and product occurring in negative. The probabilities of those. Okay. And if you do, the probabilities will be 0.00693 for positive and 0.0034 for negative. So it is set as positive. This is how basically it works. But should we do this all by ourselves in mathematical? No, it is not required. Why? There is a library known as sklearn which does all of this, and we are going to use that. So before going into training, we are going to see about the limitations, where the main limitation is that it is under an assumption that there is a feature independence which is there, because this shows that like this feature is dependent, but those good is a feature which is independent. Okay, but usually that is not the case with text data, and that is why there is a limitation with neighbors, but still it works very well in real world. Okay, so that is about the introduction for the neighbors for text classification, where we are seeing about NLP with machine learning now. Now let's move on with training a neighbors classifier with the help of sklearn. Here is a code for training a sentiment analysis model with the help of neighbors. Okay, this is how usually it works in real world. Okay, you need to use class because it is very formatted and it will be very easy to manage. Okay, and you can add your doc strings for explanation. So please try to follow this kind of a procedure. This format is known as Web08. Okay, so here we have the imports NumPy, then TF-IDF, which is TensorFlow datasets, from where we'll basically load the dataset for our training, and then train test split to split the dataset for training and testing. And then we have vectorization, which is TF-IDF vectorization. Okay, like I said, for simple text classification to create those vectors, which is your embeddings, TF-IDF is more than enough. Okay, and then for model, we are going to use multinomial neighbors, and then we'll use pipeline to combine those vectorization and model all as a single pipeline, and then job loop to save and load models or even datasets, stopwords to remove those, and then word tokenize to tokenize the sentences, and then we have regex to clean basically whatever is required. This is just a demo, so we are not expecting a very good performance and all here. Here we are creating a sentiment analyzer class, and in initialization we have max features, which is 5000, and test size is 0.2, random set is 42. All are provided in initialization. The pipeline is set to none by default, and the stopwords is the set of stopwords which are English, which we got from NLTK corpus. Okay, to understand this, what we are going to do is we are going to go through the main function. Okay, so first you are creating an analyzer which will call the init function, and we have seen what happens in the init function. So first what we'll do is we'll load the data. So here we have the load data function which will load the IMDb dataset. So what happens here? First we are calling the tfds.load function. Basically it will load the TensorFlow dataset about IMDb reviews. Okay, we are setting the with info as true so that it will provide the metadata information and all, and as supervised as true so that you will get the labels as well. Okay, and dataset of train and dataset of test is obtained from there, which is train dataset and test dataset. So what we'll do is we'll concatenate these two datasets, and then we'll create NumPy array of those. Okay, that will become your X and Y. X is your independent feature and Y is your dependent feature. Y is basically a label which depends on your X. Okay, and that is how the dataset is loaded. Okay, now you have the prepare data section. Okay, what it will do? It will basically split the dataset. Okay, so it will pre-process the text, and then it will split it as X and Y, as X train, X test, Y train, Y test, so that while testing we'll make sure that those data is not leaked, and this data is basically not test data, it is validation data. Okay, you'll validate the model, validate the performance, that how it has trained itself. Okay, now you'll call the train model function, where what it will do is it will create the pipeline first. So how the pipeline is created? The pipeline is created by calling the TF-IDF vectorization. Okay, and the max feature, if you see, it is gonna constitute about the number of embeddings. Okay, so I'm gonna represent it with 5000 features. That is what is max features all about. And once I represent those, I'll classify with the help of multinomial naive Bayes classifier. Okay, once you create that pipeline, you'll call the fit, which is basically the train function for ML models in scikit-learn, where how you'll do that? You'll do with xtrain and ytrain. Okay, so given an x like this, you'll get a y label like this. That is what is pipeline all about. Okay, now your pipeline is trained. Okay, what you'll do, you will evaluate those. Okay, so how is that? So once your pipeline is trained, you'll call the predict function on your test data set, and those will be your predictions predictions. And we'll call the classification report, which will have the precision, recall, and so on and so forth. Everything will be there in the classification report, and will also print the accuracy. So once that is done, we'll save the model, and when required, we can load the model and do inferences later. And how you'll do that? Once you get the text, you will process the text, and then the pipeline will predict the output. Okay, so this is how the pipeline is also here. Now let's see how this works. Python one_ beginner naive Bayes sentiment.py, and now it is trying to load the IMDb dataset. So it is already there in my system, so it is not downloading it. For your case, it will download it. Okay, it's pre-processing the data, and as you can see here, the dataset is already loaded with 50,000 samples in it. To process those 50,000, usually it will take some time, and it is done. Now it has split the data into training and testing. The training model procedure is happening now, and the model is trained, like in minutes. And here you can see the accuracy is around 86%. That is pretty good, right? We didn't do a lot. Like for example, to code this, right? I took only around 10 minutes actually, because it wasn't very problematic. And to get 86% accuracy, it is pretty good. If I work some things like, like text pre-processing and all, I can push it to 90, 92 easily, right? And here you can see the inference is at real time, right? Why go for advanced model for these kind of use cases? That is why I showed this in our prerequisite section. Okay, here you can see the accuracy is 8536. The model has been saved and loaded again. And when I gave in testing, okay, this movie was excellent, the acting was superb, it is said positive. I didn't enjoy this film at all. The plot was confusing and the characters were poorly developed. It identified that it was negative. An average movie, it has moments, but overall it is just okay. If I had trained it for neutral, it would have said neutral, but it gives a negative feeling, right? So it has said negative, right? And that is how you'll train your own naive Bayes classifier for sentiment analysis. In the next section, we'll be moving on with the intermediate prerequisites, where I'll be covering about RNN networks for your advanced use cases than just text classification. All right. So here you can see there are some main networks you need to see, and we'll also make a story creator with the help of RNN. That will also do. Okay. And that will be done in the next section. I hope you all like this video, guys. If you all like this video, please hit the like button, share it with your friends. If you haven't subscribed to the channel, please hit the subscribe button, hit the bell icon. This is a free course, and here you can see for prerequisites itself, I'm not even able to make, a single video. After I've made it as beginner, intermediate, advanced, because that requires that much time. For example, this beginner video itself took around 1 hour, and hereafter it is gonna take even more time because I need to explain the networks at least to some extent, so that you'll be able to understand why the LLM networks are preferred and how it came. Right? So these are all for free. All I'm expecting is just some likes and comments of yours. So please hit that. I'll see you all in the next video. Until then, happy learning. Welcome to the day 0 intermediate prerequisites. Previously, we saw about the beginner prerequisites, in which we saw a detailed introduction to NLP, which covers key components of NLP, common tasks in NLP, challenges in NLP, applications of NLP, followed by which we saw how the NLP pipeline works, after which we saw a detailed explanation on the methods which are present in text pre-processing, where for Regex alone we gave some special importance because that is even widely used nowadays. even after LLM has come into the picture. After which we moved on to embeddings, which are nothing but the vector representations of the text, where this vector representation basically captures the semantic relationship between those words. We saw the types or embedding methods which can be used. There is one embedding method which I didn't cover here, and that embedding method is something which we'll see later because that is advanced, and those concepts can be discussed only after I discuss about transformers. And then finally, we ended up with an introduction to NLP with machine learning, where we trained our own naive Bayes sentiment analysis classifier. So that was about the beginner prerequisites. Now, in intermediate prerequisites itself, it has been made as two parts. So the first part would be about deep learning on an overall aspect, like what are the aspects which are there while we train a neural network, and so on and so forth, like that. And the part two will be focused on NLP oriented networks, which is RNN. So we'll be seeing about these networks in detail later in this video. So with that being said, let's jump into the video by starting up with an introduction to deep learning, answering the questions of what, why, when, and how. What is deep learning? Deep learning is a subset of machine learning that uses artificial neural networks with multiple layers to model and solve complex problems. Please highlight the word to model. And why is that? I'll say in a minute. So it is inspired by the structure and function of the human brain. Now, what is the difference between machine learning and deep learning is that machine learning algorithms have their own predefined mathematics, and what they will do is they'll try to find the best value for a variable which is already defined in the equation, which means it is expected that your data has a linear relationship in it. Okay? But that is not the case with deep learning. How much ever complex relationship is there, how much ever polynomials it involves, doesn't matter, because these neural networks will be able to find those relationships by themselves. So that is what is deep learning. Why should we use deep learning? Automatic feature extraction, because deep learning has the capability to automatically learn features from data rather than a lot of feature engineering, which will be usually done when we work with machine learning models. Scalability, performance usually improves with larger models and more data, so it is highly scalable. Versatility, deep learning networks have a wide range of applications from text to image to speech and so on and so forth, even playing games. And it provides state-of-the-art performance in whatever domains we see. It achieves the top results. Often even it surpasses human level performance. So that is why we need to use deep learning. When do we need to use deep learning? When there is large amounts of data, we can use deep learning, because deep learning, it thrives on big data. It loves having big amounts of data. When you have complex problem, like I said, if there is a high non-linearity in your data, or there is high dimensions and you want to find a variable with the help of machine learning, that is going to be hard. So at that time, you can use deep learning. When you have unstructured data, like I said, image, audio, and text, you can use deep learning. For time series data, you can use a specific variant of neural network, which is RNN LSTM, which we'll see in detail in the later part. And then in autonomous systems also, you can use. How deep learning works, the pipeline, basically. So first you will collect the data, and then you'll make your own neural network architecture. So that is your model building phase. And then model training phase, what we'll do is we'll do a forward propagation, calculate the loss, and then we'll update the weights in the backward propagation phase. These are just introduction. Don't worry. All of these will be explained, each and every concept in detail later in this video. Evaluation, testing the model on unseen data. And then once you have evaluated, you can just deploy it. And that is what is using the trained model for predictions on new data. So what are the advantages of deep learning over machine learning? Feature learning. ML often requires feature engineering, but DL can do that by themselves. Performance with large data. Machine learning has its plateau. Plateau is something like, your curve goes like this. Let's say your learning curve is this, okay? Higher the better. Machine learning will go like this and then it will go like this, okay? But deep learning will always go like this. It always thrives with large data. Handling unstructured data. Machine learning can't do that, but deep learning can. Scalability. Though machine learning models are faster, it is not highly scalable for complex use cases, but you can easily scale your deep learning models for complex use cases by just adding layers. Transfer learning. Nowadays, if you see LLMs, we are not training the LLM, we are transfer learning. We are fine tuning the LLM. It has some knowledge to it. We are just adding some knowledge on top of it. That is easier with the case of deep learning, but with machine learning, it is very limited. So to say, it is close to impossible. And then we have parallel processing, which is something you can do with deep learning, but not with machine learning. However, deep learning has some disadvantages as well. Like I said, it requires large amount of data and it is computationally intensive. It is not as interpretable as machine learning because with machine learning, you have equations defined prior, but with deep learning, it will try to identify the equation by themselves, which means it is going to be a black box. And if you don't regularize your network and normalize your network well, it will be prone to overfitting. So depending on the problem you are facing and data available and computational resources, you can either go for machine learning or deep learning. Now, with that being said, how will you create your deep learning neural network architectures? There comes our savior, Pytorch. Pytorch, if you see, it is an open source machine learning library or deep learning library. Like I said, deep learning is a subset of machine learning. It is a library which has been developed by Facebook's AI research lab. It was created by Facebook AI, but now Pytorch is a separate organization. It provides a flexible and efficient platform for building and training neural networks, making it a popular choice among researchers and developers in the field of deep learning. There is another competitor as well, which is TensorFlow, but it is more rigid. But Pytorch is more flexible. Why is that? First, it allows you to use dynamic computation graph. The model architectures will be very flexible and easier for debugging. Dynamic computation graph is nothing but your forward and backward computation will be a form of graph where the gradients all will be stored. Okay, so that is your dynamic computation graph. Pythonic interface, the most important aspect as far as the developer is concerned. It provides a natural interface that aligns with Python programming practices. If you are a Python developer, you will be very well versed with using classes, and Pytorch expects you to use classes. That is not the case with TensorFlow. GPU acceleration. Pytorch provides built-in support for CUDA to be used for training your neural networks. Autograd system, which will automatically compute the gradient while you do backpropagation. And it has a variety of tools for CV, NLP, and reinforcement learning. These are some of the key features and reasons why developers and researchers in the field of deep learning prefer Pytorch over other frameworks, with TensorFlow being the second most popular framework right now. So Pytorch has many functionality, and here it has broadly been categorized into some areas. One is tensor operations. So at the core, Pytorch tensors are multidimensional arrays, as like NumPy arrays. So if you are wondering NumPy array, what is it? It is just normal list, but it is of NumPy, which will allow you to do complex mathematical calculations. So this Torch tensors will allow you to run it on GPUs. Okay, so let's say I have an X tensor which is 1, 2, 3, and then Y tensor where I'm calling torch.rand, and the size is 3 cross 3. Okay, so 3 cross 3 random tensor will be generated, something like this. So you will have your data like this. Okay, that is what is 3 cross 3. So how you can identify this? When you call tensor.shape, you will be able to see the tensor shape. Okay, so I'll also print that. print y dot shape. Okay, and then we'll also print z. Along with that, we'll also print w, which is just multiplying the same array on itself. So here you can see the tensor shape is 3 cross 3, and here is basically a reset where this is how it has been added. Okay, so with 1, 2, 3 being here, and if you print y, you'll be able to understand what is the value of y. Here you can see it is 0.94, 0.60, and 0.95. With 1 being added, everything will become 1.1.1. Same will be 2.3 points, and so on and so forth. Okay, that is your basic tensor operations, and all will be under Torch. Okay, and in Torch there is something called AutoGrad, which will automatically compute your gradients, and that is why I said the computation graph is very flexible. So here all you need to do is just set requires grad is equal to true, and what will happen is if I do x is equal to torch.ones of 2 cross 2, so it will generate a 2 cross 2 matrix, and then we'll add 2 to those variables. Okay, and once that is done, we'll multiply y by y, and then we'll multiply it by 3. Okay, so if I do this, here you can see I've got z.mean, and if I call backward, and then finally if I print the x gradient, this is what is my gradient. But previously if you see x, it has been 1, 1, 1, 1. This is the value of the gradients, not the value of x. All right, so that is AutoGrad. So AutoGrad is basically your differentiation, which will be used for loss optimization, which is in backpropagation. Okay, so there is an important module which is torch.nn module or neural network module, when we say it as an abbreviated form. So the Pytorch provides a high-level API for building neural networks through torch.nn module, and here is how you can implement a simple torch neural networks. So torch.nn as nn, you will import it, you will create a class or whatever you want, and you will inherit this nn.module. First, in init.self, you need to override the parent class. So you'll call super of simplenet self dot dunderInit. So here we are taking 2 fully connected layers. So what are those fully connected layers? It is nothing but those are a and n basically. Okay, and what it has is a number in represented in dimension 10 will be represented in dimension 5, but it will be learning out of those. Okay, that is how it happens with linear layers. So here if I print the model, this is how the model is. Okay, and how the forward will happen here, your ReLU activation function will be applied on fully connected layer 1 output, and then that output will be sent as an input to fully connected layer 2, which will provide the X output. Okay, so that is your neural network modules. And with data loading and processing, it is very important to know about the tools provided for data loading and processing. So the first tool is Torch Dataset. It will allow you to make a dataset of your own, and then DataLoader, which will load the data. Okay, so this is how the structure is. Don't worry, we'll see about this in detail, but just to say, these components will work together to provide a comprehensive framework which will help you to develop, train, deploy your deep learning models with ease. And Pytorch design has been emphasizing on ease of use, flexibility, performance, and then it is very powerful for both research and production environment. Okay, so those are the Pytorch functionalities, key functionalities. Okay, but there are some other functionalities as well, where, like for example, torch.optim, which contains the optimizers, which we'll see later. Okay, now jumping on to the Pytorch dataset and DataLoader. So what is Pytorch dataset? In Pytorch, the dataset is an abstract class which is representing your dataset. Any custom dataset you create should inherit this dataset class, and it will override these 2 methods. One is dunderLearn, and then another one is dunder get item. So the dunder learn will say the size of the data set is this much, and dunder get item, what it will do is once you have an index passed, the data will be returned. Okay, that is what is get item. So if you have any kind of pre-processing to be done on a raw data, those will be done in this get item section. Okay, so for example, I want to do something like this. It will be done in dunder get item. So the custom dataset class will inherit the dataset class, and here in init function, it takes two values. It is data and labels. So the length of the data is going to be length of self.data. And in get item, what we are going to do is we are going to provide the data at an index. Okay, that is what is the purpose of dataset. A dataset or a data value at a specific index in the dataset is obtained via get item. Okay, so that is what happens in torch dataset. But only dataset is not enough. Okay, it is not of any use. What we use is DataLoader. So one of the most important advantages of Pytorch is that it supports multiprocessing, and for using multiprocessing, you need to use DataLoader. What it will do is it will iterate over the dataset while it supports automatic batching, shuffling, multiprocessing, all it will support. Okay, these are the three main features of a DataLoader. So if I have a custom dataset being called with A, B, and 1, 2, I'll say my batch size is 1, and I'll set shuffle to true. Num workers you can set to how much ever you want. I don't have a lot of processors left in my system course, so I'm setting it to 0 so that it will run in single thread, but you can run in multi-threads as well. So here you can see A is printed because that is the first one, and then the label is also printed. Okay, so you can see, right? So why A and B are coming one, not in a sequence. It was A, B, A, and then another time A and then B. So why it happens is because we set shuffle to true. Okay. So what this data loader will do is this will provide the batch of inputs to the model. Okay. But this will support multi-GPU, multi-processing and all, so making your training more efficient. So basically the idea is that you will create a data set which will represent your data set basically. So it is not just a data frame, it will be a torch data set, and that will be loaded with the help of a data loader into the model. So that is what is all about Pytorch dataset and data loader. Now let's see about neural networks. What are neural networks? Neural networks are computational models which are inspired by human brain structure and function, because researchers wanted to know, replicate the functionalities of human brain, because that would be the real step towards artificial intelligence rather than with a pre-computed equation. So that is what is neural networks all about. It consists of interconnected nodes or else neurons, because neurons is the smallest functional unit of a neural network, and neurons is the most smallest functional unit of a human nervous system. Okay, so like I said, cliche, right? They wanted to replicate the human brain. So these neural networks have interconnected neurons which are organized in layers, and these are designed to recognize patterns and solve complex problems. So that is what is neural network. So why should you use neural network? So whatever we said as a reason for using deep learning, it will apply to neural network, because neural network is the reason for which deep learning became popular. Pattern recognition, it is excellent at identifying complex patterns in data because it computes the relationship equation by itself. And then adaptability, it can learn and improve from experience. Generalization, it can make accurate predictions from experience on unseen data. Non-linearity, like I said, it can model. It means it can create. That is what is the stylish way to say can model complex non-linear relationship. And parallel processing, that is also allowed. And how do neural networks work? So once you get an initial data, it will be sent to the input layer, and it will receive the initial data will be passed to the hidden layers where the real magic happens, where all the calculations are done with the help of weighted connections, and then the output layer will provide the final output. Here in between, we'll use a lot of things like activation functions. We are training it, and we'll do backward propagation, which is using optimizer and all. Okay, so that we'll see later. But the process is that you'll have a forward propagation, and how that will happen. Input layer will obtain your input, and hidden layer will do the mathematical calculation and say, like, this could probably be your output, and the output layer will say, like, this is my final result. So that is what is neural network. Now, this is how you can create a simple perceptron from scratch with the help of NumPy. So first, we are just creating a simple class known as perceptron, where we are saying, like, our input size and then the rate at which the model needs to learn. Learning rate is a control parameter where it will say, like, at what rate you want to learn. And don't worry, we'll see about learning rate later in detail in the backward propagation section. So the weights are going to be np.random.ran, like, we are just randomly initializing weights and biases, and the learning rate is already obtained here. Okay, and for activation function, we have a function called activate, and predict will be your output gate basically. Okay, so how basically a perceptron works, this is how it works, and now you won't be able to understand this. Okay, I'll say that now itself. Now you won't be able to understand this. When you will be able to understand this? Once I teach about forward propagation and backward propagation. Okay, let's see that now. Once we see about the different architectures of neural network, like, variety of neural network architectures which are available. First is the most basic type, which is artificial neural network, which will have one input layer, one output layer, and one or more hidden layers. The most suitable use cases would be classification, regression, pattern recognition, where you have a closer to structured data. Pros is that it is versatile, it can approximate any function basically, and the cons is that it will structure with spatial or temporal data. Spatial is nothing but the geographic data, and temporal data is the data which involves time as an aspect inside that. So CNNs are specialized for processing grid-like data, such as images. Okay, so the key components here are convolution layers, pooling layers, and fully connected layers. Fully connected layers are, one single perceptron, and then, like, you have replicated it as a layer. Okay, that is what is fully connected layer. Dense layer, we say it. So the use cases will be mostly involving vision related things, computer vision tasks like object detection, image classification, and so on and so forth. It will be very efficient for spatial data. So, like, when there is geography related, like, images, it will be very good. And the parameter sharing thing, which is there in pooling, it will reduce overfitting. But the cons is that when there is non-spatial data, like, for example, temporal data, it will struggle. There came RNN to solve the issues in CNN. So if you see, ANN had issues which was solved by CNN, and CNN had issues which was solved by RNN. But there are things which CNN can do, but RNN can't do. Okay, because RNN had focused on one specific issue which was there in CNN. Okay, so RNNs are designed to work with sequential data. The key feature is that the loop in the network, which will be there, it will allow you to have information being persisted towards, like, all the time. There are variants of this network like LSTM, GRU, and all. The use cases is mostly related to sequential data, which is natural language processing related task, time series related task, and so on and so forth. Pros is that it can handle variable sequence length data sets, maintaining temporal information, and cons is that it is very difficult to train due to vanishing and exploding gradient. Okay, so these are the type of neural network. Before going into these, which is creating a Pytorch simple ANN, let's see in detail about forward propagation and backward propagation, and then we'll move on to creating a simple Pytorch ANN. Okay, so for forward and backward propagation, I have provided a separate file markdown file because there is a lot of mathematics involved in backward and forward propagation. So to explain that, it is better to have a separate file. That is what I felt and I have provided here. So let's start with the forward and backward propagation now. In neural networks, forward propagation and backward propagation are the two most fundamental processes in the training procedure. Forward propagation is the process of passing the data, input data through the network layers, where you'll calculate the output and you'll compute the loss by comparing it with the actual target. Basically, what you'll do is there will be an input layer and you'll provide your input there, and then all the calculation will happen in the hidden layer and then will be sent to the output layer, and then the output will provide an output which is a prediction, and that prediction will be compared with the actual target, and that will provide you the loss, right? So that is the forward propagation. So now I've said it in an overview, but how this actually works, let's see as a step by step with a mathematical example, right? The input layer. What happens in the input layer? The process starts by feeding the input data to the network. That's all. Okay. Just providing the input data to the network. That is what happens in the input layer. Let's say we have two features. Okay. Two features is like two dimension. Okay. One is x1, another one is x2, and your target is y. And here y is equal to 1. x1 is equal to 1 and x2 is equal to 1. These are the features. Okay. Now what you will do is first you will calculate the weighted sum, or else it is also known as linear transformation. Each input is multiplied by a corresponding weight and it is summed. So if you all know what is linear regression, the formula is y is equal to mx plus c. Okay. Here the linear transformation equation would be y is equal to w transpose x plus b. There m will be your slope and c will be your constant, right? So here it is replaced by weights and bias. Okay. And by the way, we'll update those weights and biases that is there. Okay. But these are the parameters which are responsible for neural networks to learn. For neural networks to learn, we'll be updating the weights and biases. So here you can see the each input is multiplied by a corresponding weight and sum. Along with that, we'll add a bias term as well, because at times there might be a possibility that you might face 0 when you multiply, right? So at that time, now let's take an example that we have two neurons, all right? The two neurons will have weights for each, and these are in hidden layers. Okay. So the weights for the first neuron is W1 and W2, which is 0.1 and 0.6. And weights for the second neuron is 0.5 and 0.7. All right. Now here you have bias as well, which is B1 and B2. And the values are 0.2 and 0.3. Okay. So why is there two weights for one neuron? Let's see that. Here we have a sample neural network which has two input neurons. Like I said, we have two inputs, right? 1 and 2 as x1 and x2. Two hidden layers, neurons. Actually, there is only one hidden layer, as you can see here. And there is two neurons in there. Okay, that is why the representation is input layer belongs to a layer which has two neurons. Hidden layer also belongs to two neurons, and output layer has one neuron. That is what is our architecture, and this is how the neural network will look like. Okay. Now let me tell how those weights came into the picture. Here you can see there is a red line, there is a tainted blue line, and then there is another red line, there is another blue line, right? So these lines contain the weights. Okay. These lines contain the weights, and there is a bias as well. Okay. Similarly, here also, if you see, there are two weights and there will be one bias. Okay. So this is how a neural network will look like. So Here you can see if I increase the number, say it is like this, and the hidden neurons goes like this. I have another layer, let's say, and here you can see now this is a bigger neural network. As you can see, the connections are pretty huge, and yeah, here you can see there are pretty good connections between everything. All right. So this is how basically a neural network looks like and works like in a forward propagation. Now let's continue with the explanation. So we compute the weighted sum. How that happens? In the neuron 1, we'll calculate it as x into w plus x2 into w plus b1. Like I said, the w transpose x plus b, right? This is how it happens. So if I calculate, let's say the weights initially is initialized as, like, weights, you can't control it. You'll just randomly initialize it following some methods like hey uniform, hey normal, Xavier uniform, like that. Okay. So the output would be of like the first hidden layer would be 1 into 0.4 plus 2 into 0.6 plus 0.2, which will be 0.4 plus 1.2 plus 0.2, which is equal to 1.8. Now Z2 will become 1 into 0.5 plus 2 into 0.7 plus 0.3, which will become 2.2. Okay. So this is how the weighted sum is. Now what happens is, in a forward propagation, in each neuron, first the weighted sum will be calculated, and after that, that output will be applied with an activation function, because that is what is used to capture the nonlinearity. Okay, so the output of each neuron is passed through an activation function. Example, ReLU, Sigma, TANH. We'll see these in detail later. What the idea is that is, it is to introduce the nonlinearity. The ReLU activation function mathematical formula is max of 0, x. Okay. So let's say there is a neuron 1, the A1, which is the output of neuron 1 itself. Let's say, like, there is a neuron, and the first half will be weighted sum, second half will be activation function output. So the activation function output is technically the neuron output. So the neuron output of first neuron is 0, max of 0, 1.8, which is 1.8, and then max of 0, 2.2, which is 2.2. That is what is the activation function or the output of the hidden layer 1. Okay. Now you have an output of 1.8 and 2.2. What happens now is, you have an output layer, and like I showed in the diagram, there will be only 2 weights following. Okay. So there is 2 weights here, 0.8 and 0.9, along with 1 bias. So what happens here is, you will multiply with 1.8 and 0.8 together, and 2.2 and 0.9 together, plus 0.1. Okay. Finally, your output layer output is 3.52. But what was our expected output, which is 1.1? Okay, that is our expected output. Now you might wonder, okay, there is input, but there is output which is not at all related. How we'll adapt that? That is why we have the process of loss calculation and followed by backpropagation, where what we'll do is, we'll change the values of this weight 1 and weight 2 such that this output value of 3.52 will become closer to 1. Okay. Now let's see how those happens. Loss calculation is the final step in forward propagation, and how it happens is, you have a true target, which is your output or your expected output, and then you also have the model output, which we'll say like y output. Common loss functions used are mean squared error, cross entropy loss, and there is hinge loss, binary cross entropy loss, and all. But right now, let's see the most simplest loss function, which is mean squared error. Mean squared error is, the formula is, we'll compute the error, and then we'll square it, and then we'll divide by 2. Okay. So the y output is 3.52, y true is 1. So 1 by 2 of 2.52, the whole square will be 3.1752. Okay. So that is the loss right now. Now you need to reduce this loss, and that's where backpropagation, which is the second phase, or probably the more important phase in deep learning comes into the picture, which involves calculating the gradient of the loss function with respect to each weight in the network and then updating those weights using an optimization algorithm. For example, that is gradient descent. How step by step it happens. First, we'll compute the gradients for loss, and the formula is partial derivatives. We'll use partial derivatives here. Dou loss by dou output. So it will be z output minus y true. Okay, dou loss by dou output is z output minus y true, and the value would be 2.52. Now you have dou loss by dou output. Okay, now what you will do is you will calculate the gradient at that output layer. Okay, now you have calculated the gradient for loss alone. Now you will calculate the gradient for the output layer itself. So how that happens is, with respect to every weight, we'll do that. Okay, dou loss by dou weight phi is equal to, if you see the weight phi, it has been constituted with the help of activation function of first neuron's output. So we'll take that only. Okay, in backpropagation, everything happens in reverse. So activation function 1 output into dou loss by dou output, which is 1.8 into 2.52, which is equal to 4.536. So similarly, you will calculate it for dou loss by dou W6, which is 5.544, and then we also calculated it for bias, because bias doesn't have a value already. It is just a constant value. So here, for partial derivative, we'll just consider the value of dou loss by dou output itself. Now we'll calculate the backpropagation at the hidden layer. Now to backpropagate the error at the hidden layer, you should use a chain rule. Okay, the error signal at each hidden neuron is a product of the derivative of activation function and the error propagated from the output layer. So what does that mean? These values will be propagated to here as well, along with the differentiation of the output of activation function. Okay, so the activation function is relu, and if you differentiate that, if the asset is greater than 0, it will be 1 and 0 otherwise. Okay, you will never face 0 a lot of times. There are some times, and we'll see about that later, but it will be always 1 mostly. Here, if you see, everything is 1, so we need not worry about multiplying it with some 1 or 0. All we need to do is multiply the weights of 5 and 6 with this output we obtain. Okay, because this is gonna be the value which will impact the gradients at the hidden layer. So it is going to be 0.8 into 2.52, which is equal to 2.016, 2.268. Okay, now these are the error at neuron 1 and neuron 2. Okay, that is why we multiply the weights. Now what is the gradient there? So if you want to calculate the error, right, you will use the weights values of the layer plus 1. Okay, let's put that way. Let's say if it's a hidden layer and there is one output layer and then one input layer. Okay, so to calculate the output or the gradient at the hidden layer, you will use the error at output layer, and then you will calculate the gradients with the help of inputs which we obtained previously. Okay, so the calculation would be dou loss by dou W1 into dou loss by dou Z1, which is 2.016 and 4.032 in place of weight 2, and then bias 1 will be 2.016. There also, if you see, we calculated it for weight 5 and weight 6, right? Now we are calculating it for weight 1 and weight 2 because that is the first neuron, and second neuron is 2.268 and 4.536. And here, since now we have the values of gradients, we can update those values. So if I want to update a weight 1, what we will do is we'll have a learning rate, like I said right previously, the rate at which you want the model to learn. Slower the better. Okay, slow and steady wins the race is the proverb, and that works for deep learning. Okay, so the formula would be, let's say this is weight new. Okay, because you are updating that weight, right? Weight new is equal to weight old minus learning rate into dou loss by dou w, which we calculated already. Okay, so it is going to be 0.4 because that was the weight 1. So you can see, right? Weight 1 is 0.4 into minus 0.01 into 2.016, which is 0.37. Now, if you see, the weight has been reduced from 0.4 to 0.37. So similarly, from 0.6, it has been reduced to 0.55. Similarly, it will reduce or increase based on, like how you want it to be. Okay, this process will be repeated for each training example across multiple epochs until the network will converge. Okay, so in that way, your loss will become minimal. This is how basically the deep learning procedure happens. In this, as a summary, forward propagation will involve weighted sum, applying activation, calculating output, and then loss. From that loss, you'll start back propagating the gradients with respect to weights and biases, and then you'll update them with the help of gradient descent. So here it was said as a simple step that it is update of weights and bias, which uses gradient descent. Okay, gradient descent is an iterative optimization algorithm that is used to minimize a loss by adjusting the model parameter, which is weights and biases. The main idea is to move towards minimum loss function by taking small steps in the opposite direction of the gradient of the loss. What is meant by that? Let me show you. Here is a sample curve of gradient descent. Okay, if I stay here you can see the main idea is to move towards the minimum, taking small steps in the opposite direction of the gradient, which is slope of the loss with respect to its parameters. Here you can see, let's say initial weight is here. Okay, but the loss will be 0 at here, and this place is known as global minima. Okay, at real time the curve won't be looking like this. It will be like, it will be like this and this. Your challenge would be, there will be a lot of local minima here like this, but there will be a global minima here you need to attain here. Okay, that will be a challenge. We'll see about that later. Okay, now we will have those gradients, right? We already calculated those are the gradients which are here. Now your weights are here. You need to take a step by moving from here to here, and then here to here, here to here, here to here, here to here. Finally, you will achieve the minimum cost at 0, like close to 0. You will never reach 0, but you will achieve close to 0 performance. Okay, so this is how the gradient descent curve works. Okay, now let's see the mathematical explanation, because we saw a graphical explanation right now. What you'll do first, you'll compute the gradients. The gradient of the loss function with respect to each parameter, which we did before. Here you can see, right? This partial derivative we calculated, right? Those will provide the gradient. For a weight W, the gradient will be dou loss with respect to dou W. If it is in the output layer, yes, it will be directly impacted by loss. But if it is in hidden layer, you need to propagate the impact of loss from those output layer to the hidden layer. That is what we did here. Okay, first we took the output and then we impacted it at the output layer, and then we backpropagated it to the hidden layer with the output of these layers, right? So dou loss alone will be considered, but those output also impacted it, right? So we'll consider those outputs as well. So here is a sample. Okay, let's say my weight is 0.5, and then my gradient of dou loss by dou W is 0.2, and the learning rate is 0.01. So 0.5 minus 0.01 into 0.2 will be 0.498. Now it is a bit adjusted. Now it will come closer. Okay, that is the idea of gradient descent. This is how you will update the parameters. For bias also it is the same. Bias new will be equal to bias old minus learning rate into dou loss by dou B. Dou B is dou bias, right? Partial derivative calculated with respect to loss for bias. This is how gradient descent works, and there are algorithms like batch gradient descent, stochastic gradient descent, mini batch gradient descent, and so on and so forth. These are the basic optimization algorithm. There are lots of optimizers which has come into the picture, which we'll see in the optimizer section. Okay, but this is how forward and backward propagation works. Yes, I explained it very theoretically. And like I said, some explanation with the diagram that is for simple. So like just try to put some time into this document, and then you'll be able to get a hang of what is happening. Okay, so as a summary, what happens in forward propagation is it is a process of computing the output of a neural network for a given input. Why you should do that? You should do that to make the predictions and compute the loss. How you'll do that? It is by sequentially applying each layer's operation to the input data. Backpropagation is the process of computing the gradients of the loss with respect to the network parameters. And why you'll do that? It is to adjust the model parameters, which are the weights and biases, to minimize the loss. And for this, you'll use the chain rule. Okay, chain rule is what we did. Like we did it separate, and then we multiplied it. But like at real time, what they'll show is like it will be a single equation. By applying the chain rule of calculus, you'll propagate the gradients backwards through the network. Okay, this is what happens in forward and backward propagation. Now that we know that, let's see the theory behind the simple RNN network, and then we'll code that. Okay, a multi-layer RNN network, also known as a feed-forward neural network, consists of multiple layers of neurons. I showed you, right? There is multiple hidden layers when I showed you that. So there will be one input layer and output layer that is constant. But hidden layer and is like number of times you can just replicate it. More the number, better the output. And then backpropagation, just now we saw, right? It is the process of adjusting the weight. Now let's see how you can code this. Okay, this will be a sample code. Okay, don't worry, we'll train that. Pytorch provides a high-level API for creating neural networks through torch.nn module. So for that, what you need to do? You need to first define a class that inherits the nn.module, define all your layers which you'll use in the dunder init method, and then implement the forward method, which is just what we saw as forward propagation, taking the output of first calculating the weighted sum, and then applying the activation function, provide that output to the next layer, calculate the weighted sum, and if there is an activation function, calculate that, and so on and so forth till output. That is how we did the forward propagation theory, right? So that's how we'll do it in forward as well here. Let's take a simple example that we have two layers, okay? And there is one activation function for the first layer alone, okay? So the dimension here would be 10 cross 20 and 20 cross 2. Now you'll wonder, 10 cross 20 and 20 cross 2, how is this thing? So what happens is, actually you'll have 3 layers to look like. Okay, there will be 10 neurons at first, which will be projected to 20 neurons here, and then those will be projected to 2 neurons. Okay, so if I had it like 2 to 1, this will be the same network which we discussed right now. Okay, so here we have the layers being initialized as linear layers. Those layers which we said about is linear layer, simple linear layer. And then the activation function will be also there in NN module itself, NN module. So we'll call ReLU activation function. And here if you see, once we get the input, we are passing it through the layer 1, which will provide you Z1, okay? And then that Z1 will be provided to ReLU, which will be your O1, and O1 is provided to your layer 2, which is to your output, and then that will provide your output. Okay, so this is how a neural network is defined. And here you can see there are some common layers. There is linear layer, which is also known as fully connected layers. That is what is used in ANN, and linear layers generally used in any network, because fully connected layer is the only layer which has the capability to extract the information which is already there by expanding it and contracting it. Like the equation it calculates, it is very versatile to adapt it to any domain. There is 2D convolution layer, which is used for images. There is RNN LSTM GRU for recurrent layers, which we'll see later. And batch normalization is there, and then dropout is also there. Dropout is there because you don't want your model to memorize things, right? So at that time, what we'll do is, it is a normalization method where what you will do is you will just drop some of the neurons. Let's say you have 10 neurons in one layer. You have provided the probability of dropout as 0.2. What it will do is it will keep 8 neurons and 2 neurons output will not even be considered, considering that that is a dropout neuron. Batch normalization is the process of normalizing the values or inputs which are provided to that layer. Okay, that is batch normalization. Activation function, there are common activation function like ReLU, sigmoid, tanh, softmax, and for loss, MSE, cross entropy, BCE loss, in optimizer, stochastic gradient descent, which we saw already, a variant of gradient descent, and then there is ADAM, RMS prop and all. Okay, so a training loop example will look like this. First, you will get the loss function, you'll initialize your optimizer. So what you will do is, you'll go through the number of epochs. For each epoch, you'll go through the inputs which are there in the data loader. You'll get the model outputs. You'll calculate the loss. You'll first set the optimizer to 0 gradient. Optimizer is nothing but the gradient descent algorithm which we saw. Okay, and then you'll call the loss.backward. And the good thing is the loss.backward will compute all those partial derivatives we spoke about. Okay, so the backward propagation will be done and the model weights would have been updated. Now you'll call the optimizer.step function, which will complete that procedure. Okay, backward propagation will calculate those gradients and the updation will be done with the help of optimizer.step. This is how a basic training loop will happen. Okay, now we saw a simple code explanation. Now let's train a simple RNN network itself. Okay, here I have imported Torch. From torch.neural network modules, I have imported it as neural network module, and then we have imported torch.optimizer as optimizer. From data utils, we have taken Dataset and DataLoader. From sklearn.model selection, train test split is called, and then NumPy is imported as NP. You have a random dataset class. Okay, like the class, why I named it as random dataset is because I'm just generating random values for X and Y. Here the thing is, there is only one input feature and one output feature. Based on this input feature, it should say an output. Okay, that is what is the expectation here. So I've just provided as X and Y, where len will be X, len of self.x, and when you call an index, it will provide the value of X at that index and value of Y at that index. Okay, the neural network we already saw there, right? That is what is the neural network here. And then we have 1000 samples which we need with input sizes 2. So why it is input sizes 2? We need to provide it to a layer which has 2 neurons as hidden size, sorry, input size. Okay, and then we have the number of classes which is output as 2. Okay, that's why we keep it output size as 2. Hidden size doesn't matter. Okay, so here it will be 1000 cross 2. And then here it will be 0, 2, 1000. This is how it will be. Okay. And now here, if you see, these are the variables or hyperparameters. Input size is 2, hidden size is 16. So it will be 2 cross 16 here and 16 cross 2 here. Okay. And the learning rate is 0.01. I want to train it for 100 epochs. And the batch size is 32, it seems. Okay. So for every 32 samples being processed for one step, 32 samples will be processed, and at that time one backpropagation will happen. Okay, so that is mini batch SGD. Okay, so generate data, you will generate the data, you will split it as train test with the help of train test split. You are creating it as a torch data set, then making a data loader out of it. And then you are creating the model. The loss function is cross entropy loss because it is a classification problem. When to use which loss when to use which loss, we'll see that later. Because for each of those components already I have a dedicated section. Activation function, loss function, optimizer, gradient descent. For each of those, I have a separate, sections for us to discuss with. Okay. Let's not consider that right now. You have your cross entropy loss right now, which is criterion. Your optimizer is ADAM optimizer, where you'll provide the model parameters for it to optimize along with the learning rate. Okay. Model parameters will provide the weights and biases. for the optimizer to optimize with. Okay. So in the training loop, for epoch and range of epochs, so for every epoch, we'll set the model to train. At that time, let's initialize with the loss being 0, and we'll go through the training data loader to get the X and Y value. We'll send the X batch. So what the data loader will do is it will create the X batch and Y batch with 32 values in it. Okay. 32 X values are sent to the model, which will provide 32 outputs, and that will be computed as loss with 32 true outputs. Okay, now you have your loss. Make sure that the optimizer doesn't have any gradients in it, because if it has, the updation will be wrong. So first set it to 0 gradient, start the backward propagation to calculate the gradients of loss, and then call the optimizer.step function to update the weights of model, like weights and biases, basically model parameters. Now we are just adding this loss so that we can print it. And this is how the inference code is. Okay. Here, if we run this, so it is taking some time. Now you can see it started and the loss ended up at 0.68, and apparently the accuracy is 52. It doesn't matter. Like, this is just for me to show you, how it works, because this is very random data. So we can't expect any performance out of it. Okay. So yeah, that is how a simple ANN works. Now, what are the components we spoke about? Like weights and biases are there. That's something we already spoke about. There is activation function, which will be the first thing in forward propagation, and then you have your loss function, which will be calculated, and then backward propagation happens, and then you have your optimizers, in which gradient descent itself is an optimizer. Okay, so for each of those components, we are going to see what are each of those, why should we use those, how should we use those, and types of each of this component. And for those as well, we'll see in detail explanation. So let's start with the activation function. Activation function are mathematical equation which will determine the output of a neural network. Key thing, highlight this. It will determine the output of the neural network, because that is what is the key for calculating and capturing the nonlinearity in the data. So they are applied to the weighted sum of the inputs at each neuron. I told you, right? Calculate the weighted sum and then apply the activation function on it to get the output. So that is what happens here in activation function. Why you should use activation function? It will introduce nonlinearity, like I said. It will normalize the output, keeping it in a specific range. For example, with ReLU, it is 0 to any positive number, because we don't want any negative number. That is the idea of ReLU. But there is options like sigmoid, which is 0 to 1, or tanh, which is minus 1 to 1. Okay, that will normalize the output, and it will enable the back propagation as well, because many activation functions are differentiable. That will allow the gradients to flow backward through the network. Okay, any function which is differentiable alone will allow back propagation, and activation functions are differentiable. How these would work? They'll take the weighted sum of the input neuron and apply a mathematical operation based on what activation function it is, and it will produce an output. This output becomes the input for the next layer, or final output will be out of the network. That also will be coming out of activation function. Now let's come to the type of activation function. First, most common activation function, which is sigmoid activation function. A sigmoid activation function is a S-shaped curve that maps any input values to a value between 0 and 1. Let me show you the curve for each of these type of activation function. Now, this is how the curve of sigmoid will look like. Okay, it is an S-shaped curve which will map any input values to a value between 0 to 1. Okay, and how it will map that? It is by using this formula, which is f of x is equal to 1 by 1 plus exponential of minus x, which is e power minus x. Okay, why you should use sigmoid activation function? It is useful for the models when you need to predict the probability of an output. As soon as I say probability of an output, you might ring it as classification, maybe. Yes, if you have thought it like that, then good enough. It is for classification. Okay, but since it is 0 to 1, it is good only when it is binary classification. Okay, it is historically popular but less used in hidden layers because it can map only between 0 and 1. That is not a case which you will see with the help of normal linear networks. But this network is used widely in a very advanced network, which is LSTM. Okay, there it serves a different purpose. We'll see that in LSTM section. Okay, so there is another activation function which is tan h, and the formula is exponential of x minus exponential of minus x by exponential of x plus exponential of minus x. Okay, or if you want to say it conventionally, it is e power x minus e power minus x by e power x plus e power minus x. This is how the formula of tangent, hyperbolic tangent or tan h is. And here, why you should use that? See, this is not a zero-centered curve. Okay, it is 0.5. It is not a zero-centered curve, but it is zero-centered curve here. So the derivative will be even better. Okay, and it will often perform better than sigmoid in hidden layers because it has a range of -1 to 1. More the range, better will be the value. Okay, with hidden layers. And this is how the curve is. As a comparison, the sigmoid will go like this, 0 to 1, but tan h will go like this, -1 to 1. Okay, and you will initialize it like this. Okay, so if I call it here, my activation input will be 0 and 1 now, and then I'll be converting it to float, and here output will be 0.5 and 0.7311. How this output was calculated? It is by following this thing. Okay, this calculation, 1 by 1 plus e power 0, 1 by 1 plus e power minus 1. Okay, something like that it will happen, and then it will provide you the sigmoid output. So similarly, we can do it for tan h as well. So we will call the tangent, hyperbolic tangent activation function, and then if you print the output, it is 0.000 and then 0.7616. Okay, so that is how it happens with hyperbolic tangent. But with linear unit, which is rectified linear unit, that is what is ReLU, it returns 0 for negative values and input value will be positive for positive values. Now, why you should use this? You see, exponential is a component which is very computationally intensive. Okay, that was the case with sigmoid and hyperbolic tangent, or tan h in short. But rectified linear unit is a formula which uses max of 0, x. Like max value between two values calculating is very efficient. Okay, so that is one thing. And then if you continuously differentiate a value between 0 to 1 or -1 to 1, there is a very high chance that it will go to 0. Okay, in backpropagation, I said, right, you'll propagate the gradient and then you'll do differentiation. If you see, our weights reduced, right? The gradient value is reduced. At some point of time of continuous reduction, it will go to 0. Okay, that is vanishing gradient. Okay, at that time, your model will stop learning. And then this also induces sparsity in the hidden unit because, like the values are like that, basically. How? There is a sigmoid curve here. If you see, it is 0 to 1. But with ReLU, it is 0 to n. Okay, like, it is infinity. So if I do this, it will be 0.0 and 1.0. So you can see 0.0 and 1.0, right? But there was a problem with ReLU. ReLU had a problem of having 0 for negative values, and that created an issue known as dead neuron. Okay, to solve that, they attempted a new method which is leaky ReLU. Okay, dying ReLU is what they said it as, or else that specific issue was known as dead neuron. Okay, where the neuron, once it gets stuck, right, like once it goes to negative, it is not going to become like positive, because we'll always multiply it and it will become 0. After that, there will be no training. Okay, so what we'll do is we'll multiply it with a small, very small value for negative input. The formula will be that it is x if x is greater than 0, and if x is less than or equal to 0, you'll multiply it with an alpha value which is 0.01. Okay, it will be like this. The leaky ReLU curve will be like this, where ReLU was like this. Okay, so if I give this here output, it will be the same as before, but to compare, what we are going to do is output, let's put it as ReLU out equal to ReLU of -1. Sorry, torch.tensor of -1. Torch.tensor of -1. Then we'll see that. Okay. So you can see it is 0. Okay. But if I do leaky ReLU of torch.tensor of -1, it will be something like -0.01. Yeah, it isn't implemented. All I need to do is -1 point. Now you can see here, it is -0.01, right? It is giving some value, which is very less, right? 0.-0.01 is very less. But, like it will make sure that the training continues. That is what is the advantage with leaky ReLU. If you think that, there might be a possibility for having a negative value, go for leaky ReLU. Now, softmax, a very important activation function, which you will use it very widely, even in transformers. So what it does is, it will convert a vector of real numbers to a probability distribution. Okay. So it is used in output layer of multi-class classification problem. And then it will ensure that all the output values are between 0 to 1. E power x by summation of e power x, till j. So this curve will also be like sigmoid, okay, since it is 0 to 1. And what it will do is basically, if I print the output here, you'll understand. See here, the probability value of 0 is 0.2689 and 1 is 0.7311. Okay, that is what it is trying to say. The calculation is happening like this. Okay, basically what it is, let's say I have a multi-class classification problem of 10 classes. Okay, so what it will do is the network will say like, these are the values, or like, logits, that's what we say, for each class. Now you need to convert it to a probability between 0 to 1, and for that it will be applied with softmax. So basically, if you see, it is 0 plus 1 divided by value. Okay, that is what happens. Okay, that is what happens here. Number by summation of all the numbers. Number by summation of all the numbers. That is what it happens here. Okay, so if I print the activation input, we'll be seeing, right? Okay, I hope you get that. So e power 0 by summation of e power 1. So summation will be like, let's do that. E by E1. This is how it would be. Okay, because it is e power 0 plus 1. Okay, I hope you get that. So this is how the calculation will happen. If it was, let's say, 1 and 2, it would have become E1 by E3 and then E2 by E3. This is how the calculation will happen. Okay, now like I said, the gradient will flow through this activation function, so you will differentiate it. Okay, so this is how the calculation will happen for most of the activation function, which is there already here. So here you can see there is binary step, logistic. Logistic is nothing but your sigmoid. Okay, there is tan h, arctan, ReLU, PReLU, eReLU, soft plus, like everything is there along with the derivatives. So if you plot the curve of derivatives, this is how it would be. Okay, tan h will be 0 to 1 range, sigmoid will be 0 to 0.25, and like sigmoid of 2.5, that will be like a sharper curve. And then tan h, like I said, it is 0 to 1. ReLU will be like 0 maximum, like it will go on. It is not just 1, it will go on, like 0 or 1. There is nothing in between, either 0 or 1, because any number differentiated, it will become 1. Okay, that is what is differentiation, right? And then there is soft plus and Gaussian activation function, which will be like derivatives curves will be like this, 1 and then like this. Okay, so when you should choose which activation function? For hidden layers, ReLU will be a default option, or else like if you feel, like I said, there might be a negative value in there, choose leaky ReLU. For binary classification, sigmoid. For multi-class classification, softmax. For regression you can use linear activation, or you can use ReLU as well. because relu, if you see, it is a kind of linear activation function if the value is above 0, because it will just provide the same value. Okay, so now we are done with the activation functions. All right, let's move on to the loss functions. What are the loss functions? Loss functions are the measure which will be calculated by the difference between predicted output and the actual target. This will quantify the model's performance. If you are this much deviated from, like your target, then you have some issues, right? That is your error. So that is what is loss function all about. Why you need to use loss function? This will become a guide for you in the learning process by providing a scalar value, like, a quantified value that will show that, like, you need to be minimizing this value during training. And how these loss function work is that they'll compute a score based on the mathematical formula it has by mapping the model prediction and true value as the values variables, like, to that variables they'll map this, and that score will be used to update the model's parameters. So let's see about the types. First thing is mean squared error. A loss function that measures the average squared difference between predicted and actual values. This is usually good with regression problems. And when, like, why this is a very good error is it will penalize the large error more heavily since you are squaring it, right? The large errors will be more heavily penalized, so that it will know, like, yes, I have long distance to go. I need to, like, optimize myself faster, like that. And it is differentiable, making it suitable for gradient based optimization. Every loss function will be mostly differentiable. Okay, how this will be calculating? First, you'll calculate the difference between predicted and actual value. You'll square those, and then you'll take the mean. Okay, if, for example, here there is 3, right? You will first calculate the difference between these. So it will be 1, and then what you will do is you'll calculate the square, which is 1 again, and then it will be 1 by 3. Okay, so it will be 0.33, something like that. Let's try. And if I print this loss, it should come as 0.33 if I'm not wrong. Yeah, here you can see it is 0.33. Okay, that is how mean squared error works. Cross entropy loss. This is a loss which is very important because in transformers, everything is a classification behind. Okay, so you'll use cross entropy loss and softmax activation function. Those two are very important as far as LLMs and transformers is concerned. So please, have a better concentration in these two components. A loss function that measures the performance of a classification model whose output probability is between 0 and 1. Why you should use it? It is very suitable for multi-class classification problem, and it will work very well with softmax activation in the output layer. How you will use that? First, you need to apply softmax to the model's raw output so that you'll get the probabilities between 0 and 1. You'll take the negative log likelihood of the predicted probability to the correct class, and then you'll average that across the sample. That is how cross entropy loss function works behind. Okay, so right now what I'm doing is, instead of, like, having it as 0 here, it was 0, 1, and then 0, right? So instead of 0, I just change it to 0.7. Okay, so if you see the loss now, it will be 0.7461. Okay, so if it was 0 itself, it is 0.55. Okay, so that is cross entropy. And binary cross entropy, it is a special kind of cross entropy where it is for binary classification problem. Okay, so since it is binary classification problem, sigmoid activation function will be very good at the output layer. And how it works, it will be the same as cross entropy. Instead of softmax, apply sigmoid, calculate the negative likelihood, and then you'll have your loss. So you can see it is 0.5665. Okay, if you see here, these two are very close, right? 0.55145665, because for both of these values, now I provided, a binary classification kind of an output, 0s and 1s. Okay, that is how the optimization, loss functions are. Now let's move on with the optimizers. What are optimizers? Optimizers are algorithms which are used to adjust the network's parameters. If I say network's parameters, it is about weights and biases to minimize the loss function. Why you should use optimizers? It will implement different strategies to update weights, which can lead to faster convergence or better generalization, so that the model will update itself to wide range of um, scenarios. How do optimizers works? Once you compute the gradients with respect to loss, this will update the parameters, and with respect to the parameters, it will update them accordingly. Like I said, when you call the loss dot backward, all those gradients will be calculated, and the updation will be done with the help of optimizers only. Okay, the optimizer types of stochastic gradient, Adam, and RMS prop. These are the three main types of optimizer. There are other types like Adam with weight decay, ADA, grad, and so on and so forth. But we are gonna focus on these three alone. Okay. Stochastic gradient descent is one of the most basic form of gradient descent, which will update the parameters based on a gradient of the current mini batch. What is the mini batch? For example, I had a sample of 1000 here, right? I had 1000 samples here, in which we took 32 as a mini batch for one step. We'll update the value only for based on those 32, right? So that is what is optimizer, which is SDD optimizer, like mini batch SDD. That's what they call it. Why you should use that? It is simple and memory efficient. It can escape the shallow minima due to its stochastic nature. So basically, gradient descent will go like this, right? 1, 2, 3, 3, 3, something like that. But stochastic gradient moves like this. If it is a circle like this, it will move like this. Okay. So it can escape the local minima a bit. So how this will work? You'll compute the gradient, and you'll update each parameter by subtracting the linear learning rate multiplied by the gradient. Okay, that is what happens with SDD optimizer. And if you print that, these parameters will be shown. Okay, the learning rate is 0.01, and then there is momentum as well. Okay, in SDD there is momentum as well, but if you want, you can provide that, or else you can just leave it. Okay, we didn't provide weight decay as well. So this is the most basic form of optimizer, and this is a revolutionary optimizer. This is the optimizer which is used even nowadays, but it was found long back. It is an adaptive learning rate optimization algorithm that computes the individual learning rates for different parameters. So what it will do is, initially it starts with the learning rate, and then it will update the learning rate also. Okay, so here it will combine the benefits of two optimizer, which is AdaGrad and RMS prop. RMS prop, we'll see about that here. And there is issue with AdaGrad, which is diminishing learning rate. That was solved by RMS prop, but there were some other benefits with AdaGrad, which also was included with Adam. Okay, this will work very well with data where there is no noise or sparse gradients. So basically, Adam can be used anywhere. How it works, it will be maintaining a moving average over the gradient and the squared gradient, and those will be used to compute the adaptive learning rates for each parameter. Okay, so that is what Adam optimizer. And RMS prop is an optimizer that adapts the learning rate again based on the gradient history like Adam, but what it will do is this will just maintain a moving average for the squared gradient, and then it will divide the learning rate by the square root of this average. That's all. Okay. So that is how RMS prop works. We don't want to go into details a lot of optimizer. That is why I'm just simply saying this is how it works. Finally, we have gradient descent. That is an optimizer by itself, but gradient descent is something we need to spend some time on. So that is why I said it. It provides a way to find the optimal parameters that minimize the solution. How it will do that? We know right? We know right now about that. We'll compute the gradient of the loss with respect to each parameter, and then we'll update those in the opposite direction. The types are batch gradient descent, which will be doing it for the entire data set. Mini batch gradient descent is doing it for small batch, which we saw. Okay, stochastic gradient descent will do it for single sample. This is the difference between each. Mini batch SGD, what it will do is it will do the stochastic gradient descent on a mini batch which we provided. Okay, otherwise the formula is the same for each and one of these. Okay, so now you have a initial idea about ANN, all the components which are involved in a neural network training. In the next part, we are going to see about RNN networks, because these play a major role with natural language processing, because RNN were created for sequential data, and NLP is basically about sequential data. Okay, text is sequential, right? So in the next part, we are going to see about that. Hello everyone, welcome to the Intermediate Prerequisites Day 0 Part 2. So now we are going to see about the RNN networks in detail. In the RNN networks, there are 4 primary networks which we need to know about. One is the first RNN network which came into the picture, which is RNN by itself, and then others were modified out of it, which are LSTM, and then BiLSTM, and then GRU. All are RNN networks, and we are going to see about these networks in detail. Let's start with the recurrent neural network. So, what is recurrent neural network? Recurrent neural network is a class of artificial neural network. All were derived from ANNs only, which are designed to work with sequential data. Unlike feed-forward neural network, which is your ANN, RNN have connection that forms directed cycles, allowing them to maintain an internal state or memory from previous inputs. So what is this definition all about? Just forget these, all right? From x0 to xn, just consider that xn is your input and there is an ANN cell here, okay? And then there is dense and then output is obtained. This is how an ANN works. But with RNN, what they did was, if there is a sequence of data, let's say your batch has 5 inputs, okay? You have stock price prediction as your use case, and you have your close prices of past 5 days, and you want to predict the next days, okay? So first you will send the first day's price in x0 along with the date, and then you will send second day's price in x1, where the first day's price information is also provided to the second day's, okay? There will be a recurrence inside, okay? And that is what is shown here. If you give a xi, the si, which is the state of RNN, will be recurrently provided to the RNN cell itself, and the final output will be obtained with the help of dense network. So I hope you are able to understand, okay? In case of ANNs, there will be only dense network, okay? There is no recurrence inside that, and since there is a recurrence of state going on behind, that is why it is called as a recurrent neural network, right? Now, it begs the question, how and why the model was created. Yes, there were good models like ANN and CNN, but why RNN came into the picture? So RNNs were developed in the 1980s to address the limitation of traditional neural networks in processing sequential data. If you are processing a sequential data, it is very important that you remember the past, which is your sequence. That is not something all the previous models, which were like ANN, CNN, your machine learning models, any of those models couldn't remember the sequence. So they thought, okay, let's create a network which will do that. So for that, the motivation was to create a network that could use its internal memory to process a sequence of inputs, which will be making them suitable for tasks like speech recognition, language modeling, and so on and so forth, wherever there is a sequence of data involved. So basically, NLP, if you see, is all about a sequence. I'm talking now, and I'm talking in a sequence, right? There is a word after a word, or if we see as the model, there is a token after token, right? So the key motivation was to create a network that could use the model's internal memory itself to process those sequence of inputs, which makes them suitable for tasks which involves NLP and also time series, because time series is also a recurrence, right? Now let's see how the model works. All right, what is the basic structure? An RNN consists of input, hidden, and output layers. That is very usual. The hidden layer has a self-loop connection which allows it to pass information to from one step to the next step. Like I said, x0 is one time step, x1 is the next time step, and x0 output state is provided to x1. Similarly, it is provided till xn, right? There is a recurrence. So that is what is said as loop here, self-loop connection. So forward pass, how it happens. Let's say there is a time step t. The RNN will take an input xt and there will be a previous hidden state. Hidden state, let's call it as h. Okay. And since it is previous hidden state, we'll call it as t minus 1. So ht minus 1. So to compute the current hidden state, why we are calling it as current hidden state rather than output is because here we'll compute for RNN cell, not the dense network. Once it passes through the dense network, that is when we'll get the output. Usually dense networks are very good with one thing, which is to aggregate the information or expand the information which is already there. Okay. So right now we are looking to extract the information across temporal division, okay, which is time. That is why we are calling it as hidden states, okay, rather than outputs being passed. So to compute the current hidden state, the formula will go like this. If your current hidden state is ht will be calculated by tan h, which is an activation function, will be equal to, ht is equal to tan h of weight of hx, okay, into xt, which is just your wx transpose plus b. That's what we do, right? So that is what is here. But what we'll also do is we'll also provide the weight of hidden state of previous time step. That is why it is whh star h of t minus 1. Okay, so that is what we'll do. That is what we'll do. Every state will be calculated by adding up the information which was there in the previous state. Now you might wonder, what happens if I move 10 states before? You see, there is an advantage and disadvantage in there. The advantage is that you will reduce the computation and it would not be required as much because that previous state would have the information of all those previous states and so on and so forth. There is a sequence, right? But it is also very important that the first information comes to the last as well, because every hidden state processes it in a different way, right? That is a problem in recurrence. It will happen with the previous time step alone. Okay. So here, if you see hx and hh are weight matrices, as you all might know now, and bh is bias. So this is nothing but tan h of w transpose x plus b. Okay. And w transpose x plus b is the common function for any neural network to work with. Okay, but here what we are doing is we are adding the previous time step values also, that is by whh star h of t minus 1, right? So that is how the forward pass will happen. And if you know the forward pass, that's how the model works indefinitely, right? It will go on and on. So how the output computation will happen? If you are doing inference or final output, something like that, the output yt is computed based on the current hidden state. Like I said, you will compute the hidden states till that timestamp, and the output will be computed as why. Y is a weight matrix of your output into h of t plus b of y. Okay, this is as similar as this, but here the hidden state of current time step, which is calculated here, is provided here. That's all. And where this output computation will happen is, it will happen in dense network. Okay, that is why I said we are calculating the RNN cell forward pass here, and the output computation will happen in the dense cell. Okay, so that is your output computation. And then how the back propagation will happen? The back propagation will happen through time. Okay, RNNs are trained using BPTT, which is back propagation through time network, where what it will do is it will unroll the network through time and then it will apply the back propagation. Because if you see, we are going everywhere one state before, right? Hidden state before. So it will also do the back propagation like that, one state before. In everywhere, for the previous state also, back propagation will happen, tracking back to the 0th cell of 0th state. Okay. That is how the back propagation through time will happen. And what happens is, after each time step, once you compute the gradients, it will be summed up together. Okay, so that is how the backpropagation through time happens. And then you have your gradient flow. How the gradient flows? During training, the gradients can vanish or explode as they are propagated back through time, making it difficult to learn long-term dependencies. Like I said, it will flow through time, and since it is flowing through time, if you know backpropagation is kind of using differentiation. Okay, and with differentiation, always the value will become lesser. So at some point of time, there is a chance that it will either vanish, or if it has some weird weights, exploding is not something which will happen commonly. But if there is some weird weight initialization, there is a possibility to explode the gradient as well. Okay, so if you see as an example for RNN in a character level language model, which is to predict the next character, each input xt is a character. Like I said, one character will be xt, and the network will predict the next character, which is yt. And the hidden state ht captures the context of previous characters. For example, if I say example, right? Let's say our current hidden state is, or like our current sequence timestamp is m. Okay, so exa all will be there in the hidden state. M will be my xt, which is the current character, and the idea is to generate p, which is the next character. Okay, that is how RNN basically works. If you are using a character level RNN, when can you use RNNs? RNNs can be generally used when you have use cases like time series prediction, natural language processing tasks, whatever it is. Okay, again, these are the state of the art models then. So if we are seeing it now, yes, we'll feel like, okay, this is boring, like, the performance is not that good. But imagine that these happened in 1980s, right? At that time, these kind of models are pretty huge. These were revolutionary models then, right? So those were used for natural language processing tasks then, and it can be used for speech recognition, music generation, because all of these are working on a temporal dimension. Now let's come to the advantages and disadvantages of this model. Because to know the limits of the model, it is very important, right? Or else you can't use it for your real use cases. So it is very important to know the advantages and disadvantages. So what is the advantages of RNN? It can process sequence of variable length. Like I said, all it cares about is a sequence, and the previous time step value will be provided to the current time step. That's all, right? So it can process sequences of variable length. It will share parameters across time steps, which means it will reduce the number of parameters to learn. Okay, and then we have the capability to capture temporal dependencies in data. Temporal is nothing but time, right? So these are all something we know. So what are the disadvantages? First, like I said, since you are doing backpropagation through time, there is a problem of vanishing or exploding gradient problems which might occur. And then there is difficulty in capturing long-term dependencies, because let's take ourselves as an example, and then we'll be able to understand what happens with RNN. Okay, RNN expects on the fact that you should remember all the things which happens previously. Let's say I put you to the task of remembering what all you learned from your first grade till 12th grade. Okay, you need to remember each and everything. Would you be able to remember that? I can't remember. Maybe you can, but still it is very difficult, right? So that is why it is very difficult to capture the long-term dependencies. It is computationally expensive for long sequences, right? Because you are calculating each and every time step, right? If I go for 1,000 token sequence, you will remember all the hidden states of all the 1,000 tokens when you are coming to the 1,000th token. Okay, so it is very computationally expensive because it is very additive in nature, in sequential rather than parallel. Okay, why I am stressing on that, you will understand when we go to the next section. Okay, now let's see about another model which was more revolutionized in any field which involved time over RNN, which is LSTM. So LSTM network is a network which revolutionized a lot of things, which when it came, because it applied a special form of RNN to capture the long-term dependencies. You see, if we want to remember the old things, we'll try to forget not important things, and then we'll remember those things which are very important for us alone, right? So that is what even LSTM does. It will selectively forget and remember informations over time. Okay, let me first show you the image in detail. So yeah, it is a bit blurry because I have scaled it, but yeah, I hope I'll be able to explain it correctly. Okay, so here, this is how the RNN network is. All right, and here if you see, here you have an X here, right? This specific place is your forget gate. Okay, and here this specific place is your memory gate, and this is your output gate. So it has three gating mechanisms. And why is that? Why is this forget gate, why is this memory gate, and why is this output gate? We'll see about that. Okay, that is for detailed working explanation, but this is how the architecture is. Okay, so let's start with how and why the models were created. So LSTM, if you see, was introduced to address the vanishing gradient problem, like I said, which was there in the traditional RNN, because over time the gradients will be vanished because you will differentiate the gradients at every step. The goal was to create a model that could learn and remember information over sequences, which is crucial for any real world applications, which is using time steps, right? So basically how the model works, let's see that. Okay, an LSTM cell will consist of a cell state and three gates. Okay, so what is the cell state? This is your cell state, C. Okay, the C is your cell state, and in the cell state, along with that, you have three gates, like I said, which is forget gate, input gate, and output gate. Forget gate, what happens in there? Sigmoid of weight of F timestamp, weight just forget F. Okay, weight star previous hidden state, comma, current state. Okay, current value. So this is nothing but the similar thing which happened in RNN. Okay, you will multiply these and then finally you will add the bias. Okay, but what here happens is we'll make a sigmoid. Okay, so before going through that explanation, let me show you what happens here. Okay, let's say a variable is coming up here, or the current time step. Okay, and here there will be some previous time step informations. Okay, and this is your memory channel or cell state. Here what happens is, once a current value appears, let's say there is about 10 time steps which is stored in this hidden state information, which is also there in the cell state. That is fine. Here what we'll do is, in that 10 state, we'll add the 11th state, which is the current time step, and then we'll multiply with W transpose X plus B in that format, and then we'll apply a sigmoid function. If you see the sigmoid function, its differentiation range, activation function range is 0 to 1. Okay, so if the value is 0 to 1, what happens is we'll round it. Okay, 0 or 1. If you want to forget it, this information will be forgotten because here there is a multiplication. It will not be added to the memory channel, which is the cell state. I hope you get that. There is a cell state and you're multiplying the current values here. Okay, so we are just basically multiplying and we are saying okay, see, I want to forget it or I want to remember it. Okay, that happens in here. So I've forgotten things which I need to forget. Now what I'll do is, how much I need to remember. You see, again, if I need to remember or not, that will happen in the sigmoid function. But how much should I remember? That is something we need to check, right? Because how much should I give importance and remember is something even we do, right? Like if we say there is a very important question, we'll read it again and again for 5 times. so that we'll remember that for a longer time. So that intensity is provided by the tanh layer. Okay. So what happens here is the sigmoid will say like, how should you remember or not? That is like as same as the forget gate. But when you do the same process, rather than applying sigmoid, you'll apply tanh. The tanh range, activation function range is -1 to 1. And here, so if it is -1 to 1, you will know like, the intensity. Should I remember it negatively or should I remember it positively? If so, how long should I remember it or how much I should remember it? If it is close to -1, I need to negatively remember it, right? Like, this is something which is an anomaly. Okay. So let's say there is, stock price, there is some price going down. I need to negatively remember it. Okay. I should not sell here. I need to buy here. Something like that. Okay. And if it is going upwards, I need to remember it positively. Something like that. Okay. That is what happens with tanh. So these values will be multiplied. So if I want to remember information, it will say 1, and how much should I remember? It will be set by tanh, and those will be multiplied and then will be added to the cell state. Okay, that is what happens in the memory. Okay, in output gate, what we'll do is we'll again see if this is something which is constituent to provide output, that is by sigmoid, and then the value which is there in the cell state, because that is what is your, let's say, your brain memory. Okay, this is your brain memory. You have all the informations of your previous occurrences. Let's say what you'll do is, again, you'll apply the tanh activation function, and then with this just tanh activation function, this is W transpose X plus B, on top of which tanh is applied. That's why it is in a box and that is orange. Okay, that is a layer, but this is just tanh activation function. Basically, whatever value is there in this cell state, it will be computed with tanh, and those values will be multiplied. Okay, and finally, whatever you need to remember and how much you need to remember, those will be remembered, and that will be applied to this output, and your hidden state is obtained. This is how LSTM works. I know this is complex, but just remember that you are learning. If you want to forget, you'll forget it, right? You'll just ignore those. You are filtering it, right? Like, I'm not even gonna read this. So that is your forget gate. So if you want to remember it, let's say you'll have negative memory and positive memory, right? The tough questions you found it hard to remember, you will remember it negatively. Okay, I was struggling hard to learn this question. So that kind of memory is provided by memory gate, which you will add to your brain. And finally, based on those knowledge, you'll try to answer a question which is provided at timestamp T, right? So that is how it works in real time, right? So those knowledge, you are trying to use it and you are providing the current output. Okay, so that is how LSTM works. LSTM was actually designed based on brain. Okay, brain, how it works. On that inspiration, LSTM was designed. If you see here, actually, I didn't even spend this much time on RNN. LSTM is very important. Okay, so more than RNN, LSTMs were used a lot of times in those times. Okay, and even till transformers came, LSTM were used till, let's say, 2018. Because 2017 attention is all you need paper came, but it didn't pick up soon. Okay, so once the pre-trained models came, that is when transformers took over the market. So until then, LSTMs were the go-to model for any person who is working with NLP or time series. So here, like I said, the forget gate is to you need to forget it. Input gate is nothing but your memory gate. Okay, and this will decide what new information you want to store in the cell state. And then there is cell state update. Okay, like I said, there is star and then there is your plus and all, right? And those updation are cell state update. And your output gate, like I said, it is to apply the tanh along with sigmoid. Sorry, here you can see sigmoid layer is applied for timestamp T, and then those values, which is O of T, is multiplied with the tanh on whatever cell state we have currently. So this gate will control what information from the cell state is required for output. Okay, so that is your output gate. So example, in a sentiment analysis task, the LSTM can learn to focus on key words or phrases that indicate strong sentiment while forgetting less relevant information. So this is a very good example. Let's say I'm saying the movie was very good. I liked it so good that I watched it second time. Okay. I liked it so much. Okay. Let's put it that way. If it was RNN, it will give equal value to all of those words. Okay. But with LSTM, what it will do is it will focus on these words like very good, like, so much, which means it is a positive sentiment, right? That is how even humans do, right? We'll not focus on all those words. We'll focus on few words, and LSTM does that. Okay. So when you'll use this, which is like it is as similar as RNNs, like where RNN use cases, wherever RNNs can be used, LSTM can be used as well. So advantages is that it will capture long-term dependencies. It can mitigate the vanishing gradient problem. It has selective memory like in humans through gating mechanisms. It will have robust performance across wide range of sequence lengths. Disadvantage is that it is more complicated than RNNs, and so it will require computational resources. Okay, and then it is very challenging to train. So, like, if you don't initialize it correctly, it will not remember it, and it will not correctly forget things. So it is very challenging to find the hyperparameters which are correct to train, and then it has potential for overfitting, especially in smaller data sets, because it is very good model. It doesn't have a lot of normalization in it. Okay, so that is about LSTM. So before going into the next model, I would like to ask you all to hit the like button, share it with your friends. If you haven't subscribed to this channel, please hit the subscribe button, hit the bell icon so that you won't miss any day video which I'm uploading right now. And also, these are just free for you, but it means the world for me because the algorithm works only based on your likes and comments and your shares. Okay, so please help me with that and help me reach 10k subs. With that being said, let's go to the next model, bidirectional LSTM. Bidirectional LSTM is an extension of standard LSTM that process the input sequences in both forward and backward direction. This allows the network to capture both past and future states, which will provide more comprehensive understanding on the sequence. So if you see in LSTM, we remember the past, right? The past sequence. But let's take time series analysis out of the equation and let's put something like sentiment analysis. Okay. Let's say I have a sequence like this. The movie was very good, but I didn't like it much. Okay. Here the it refers to, the movie. Okay. Let's take another example. I didn't like it much. Okay. This is something not grammatically correct, but let's take this as example. I didn't like it much, but the movie was very good. Okay. If I'm doing it in the opposite, here the it constitutes the movie. Okay. But if you don't know what happened in the future, you won't be able to know, it refers to, the movie, and the movie was very good, so it will say positive, but it is negative, right? Because I didn't like it. So it is very important that you remember the future states as well. So that is why BiLSTM happens. Okay. So for BiLSTM, what happens is each state which we get will be sent to the next state, which happens in the forward LSTM, and in the backward LSTM, what it happens is, so those information, let's say there is your first, second, third, and fourth cell, and here the information is in forward, and backward LSTM will be in backward. So here it will be 0, here it will be 0. So 0, 1, 2, 3, 3 to 4, and 1 to 2. So the 1 to 2 information is crossed between 3 to 4. So the information is shared. Okay. So that is what they are trying to say in forward and backward LSTM. Okay. So why this model was created? Like I said, there are tasks in NLP which required understanding of the full context of sequence. Basically, NLP requires full context sequence understanding. Okay. Anywhere it is, doesn't matter. So what is the working of BiLSTM? So BiLSTM consists of two separate LSTM layers. One will process the sequence left to right, another one left to right to left, like we said. So forward LSTM, what it will do is it will be working on forward. Again, it will be based on the timestamp t-1. But since backward LSTM happens from right to left, it will be working on with t+1. Okay, so that is what LSTM forward and backward is. The output will be concatenation of the information which is obtained from the LSTM forward and LSTM backward, and based on that you will get the hidden state, right? So those hidden state again will be multiplied with the dense layer, which is going to be wy star ht plus by, which will be the weight matrix and bias vector multiplying to provide your current output at timestamp t. So while training, backpropagation will happen through time, as like in LSTMs and RNN, but will happen simultaneously for both. Okay, so it will be right to left for forward LSTM and left to right for backward LSTM. The backpropagation will happen like that. Okay, so the use cases, again, any NLP use cases can be set as a use case for BiLSTM, because it captures past and future context. It improves the performance in tasks where there is importance for bidirectional context. It reduces the ambiguity in classification tasks, and also it can be combined with attention mechanisms for even better performance. Okay, so that is a hint, as you all might know, of what might be coming up in the next video or next videos. So the disadvantage is that it is even more complex than unidirectional LSTM, because you are just replicating that again and then you are processing it in the opposite direction. Already LSTMs are very computationally intensive, and just think if you are doing it twice. Okay, and this requires the entire sequence to be available before processing. So like that makes it a bit unsuitable for real-time applications. If it is not real-time, let's say it is sentiment analysis or generation of something, like that is not real-time. What is real time is, for example, you want to real time you want to recognize what you are speaking, speech recognition. That is not something which you can do with the help of BiLSTM. So now already LSTMs have the potential for overfitting, and you are literally making another LSTM on top of that, which makes it more potential to overfitting, and then it is more complex to implement and fine tune. Okay. Now let's see about the next network, which is gated recurrent unit. Now you might see, okay, this looks like LSTM, right? Yes. GRU is a type of a recurrent neural network which was made as a simpler alternative to LSTM, because it uses a gating mechanism to control the information flow like how it happens in LSTM, but this is more simplified. Okay, and why is that? Let's see. Okay, so let me say simply how it works. Okay, first just remember what I said in LSTM, right? There was a forget gate here, okay, which will forget whatever information which needs to be forgotten, and it will add it to the cell state, right? And how much it should remember will be obtained from here, and it is provided to the cell state, and then again you will have your output gate here. Okay, so that is how happens in LSTM, right? Here the forget gate and output gate is a bit combined. Okay, so what happens is the hidden state is there, which is your cell state here. The cell state will provide the past information, and again what you will do is you will see how much you need to forget here. That is what happens here, and that will be directly provided to your update gate. Here there is only two gate. One is reset gate, which is there here, and there is update gate. Why it is reset? Here you can see it is into, right? So if you see the current time step, it doesn't use a lot of information from the previous time step. That is what is obtained from here. It will say, okay, I need to forget it. It is combining the memory gate, output gate, not the forget and output. It combines the memory and output. Okay, so here you can see it will say if you want to remember or not. If you don't want to remember, it will reset it. If you want to remember, it will not reset it. Okay, that is what happens here. And if you don't want to remember the past, okay, that information is already provided from here. Okay, this sigmoid, and how much you want to remember, that is obtained from this tanh, like we see in the memory gate, and this will be something which we see in the output gate, and those are multiplied together and are added together in the cell state, which will be providing your output. If you see, functionally this looks like LSTM, right? But there is one gate which is reduced, which is memory gate. Okay, the forget gate acts as the reset gate here, and there is output gate already. Okay, so that is your update gate. So basically your memory gate is alone not there. Memory gate and output gate are combined together as update gate. That is how GRU works. Okay, so here there is a mathematical explanation, and you can see that as well. So this gate basically decides how much information of past is to pass along the future. That is what happens in update gate, and the reset gate will say like how much information I should forget. The candidate hidden state, which is nothing but C of t, okay, which is there here. So those will have the memory content, okay, like which you need to update it to the hidden state, and the hidden state update is nothing but the plus. Okay, so basically in text classification or any use cases where LSTM can be used, you can use GRU, but make sure that the computational efficiency is the priority, not the performance, because this is not gonna be as good as LSTMs. Okay, it is not gonna be as good as LSTMs, but it is going to be very computationally effective than LSTM. That is what is the advantage. Simpler architecture than LSTM because it has fewer parameters. It is efficient at capturing medium to long range dependencies, not very long range. Faster to train and run than LSTM. Comparable performance to LSTM on many tasks. It is not better. Comparable, which means it is closer. Okay, so if you want performance, go for LSTM. If not, if you want computation efficiency, you can try GRU. Okay, it is less powerful than LSTM, so some complex task it is not good. It is less studied and understood compared to LSTMs. LSTMs, like I said, is used widely even now. So like language models are there. Even there are few people who try to use LSTMs nowadays. Performance again can vary based on specific task and dataset, and it can't do long-term dependency tasks as LSTM. Usually AI works very well when the works are separated and provided. Here like the memory and output gate are combined, so two works are done by one gate, so it is expected to not work very well as much as LSTM. So now we have an idea about the most famous kind of networks in RNN. There are networks like Peephole and all, which came and went. Okay, but these four are the most primary networks which are used in RNN, and we are seeing about these four in a brief manner. Okay, now you have an idea basically how this model works. Maybe you can work on these things and then explore on your own way for these, but these kind of information is more than enough because our focus is to learn more about the language models, right? So these information are required because that is when you will understand why language model came into the picture and why it is still good, okay, and are having more advantages over these kind of networks. So now that we have a theoretical idea about the RNNs, let's try to build a story writer with the help of RNN networks here. Okay, so don't fear that there is around 500 lines of code here. Okay, so these are just having lot of doc strings, and I have made it in that way because like if you're gonna refer the code once again and again, you can't watch this video again and again, right? So that's why the code is made in such a way that you do not need to watch the video again and again. Okay, so I'll explain the code now, and then we'll see how we can train, because here we'll see how we can write a torch dataset, how we'll write a data loader, everything will be covered. So let's jump into the code. Here you can see we have some few imports. We have torch, which is the deep learning library, the most famous deep learning library nowadays, which is used to create neural networks and so on and so forth, any kind of neural networks. And those neural networks are provided in this module NN, because Torch is a parent library, and inside that there is a module which is for neural networks, and there is Optim, which is for optimizer. Optimizer is responsible for your backpropagation, learning rate updation and all. And then you have your data, torch.utils.data, in which you will have all the data utilities, in which we'll call the DataLoader and Dataset, which is used to provide the data to the model. Okay, so first we are writing a config class. So configuration class for the text generation model, which will hold the hyperparameters and configuration settings for the text generation model. So here there is embedding dimension, which is the dimension of word embeddings. If you remember the previous section, which was beginner prerequisites, in which we said we saw that word embeddings with increased dimension, it will have more better understanding about the relationship between words. So if you are remembering it as TF-IDF, it is the max features. How much features you are gonna represent a word. Okay, so that is your embedding dimension. So higher the dimension, better the performance, but it will require more computational resources. Hidden dimension is the dimension of the hidden state in RNN, LSTM, or GRU. Okay, and then you have your number of layers. How many layers do you want? So one layer will have the cell state, which we discussed in the theory. How many cell states like that you want to replicate? Again, everything, more the number, better the result, but increase in time, increase in size, increase in computation, that will be there. Sequence length, it is opposite here. Longer the sequence length, more memory, more difficult to train, but an appropriate training length is required. Batch size. In training, each batch, how much sequences you are expecting to provide. So that is batch size. And then you have your epochs, which is the number of epochs you want to train the model on. So how much time you want to train the model. It is how much time I'm writing and seeing myself, or reading and seeing myself. That is your batch epochs. And learning rate, at what rate I want to learn. That is your learning rate. So optimizer is what will make the model to learn. Okay, so you are setting at this rate learn. And UNK token is unknown token, so you will have a vocabulary of words, and if the word is not, or if the token is not there in the vocabulary, it will say unknown. Okay, so here the values are provided. Embedding dimension is 256, hidden dimension is 512, num layers is 4, sequence length is 10, and batch size is 32, epochs is 25, learning rate is 0.001, and UNK token is UNK. Okay, so in tokenized text, we'll tokenize the input text into words. It is to just split on space, and we'll convert the whole text to lower space, and then we'll lowercase, and then we'll split it. Okay, so here if you see, let's say this is the example, hello world, how are you? It will be split as hello world, everything is in small, how are you? Okay, so that is what happens with text.lower.split. Now we need to create a torch dataset. Okay, so here the torch dataset has two things. One is length and another one is get item. Now we are doing a character level data, so which means every character will be provided. So if the data has 100 tokens, the sequence length is 10, the length will return 90. Okay, so that will show how much number of sequences are there in the data set. So the get item, what it will do is, let's say there is data 1, 2, 3, 4, 5, and your sequence length is 3. What it will do is, it will split it as 1, 2, 3 when you call 0, and it will do 3, 4, 5. Sorry, 2, 3, 4 if you call it as 1, and then see, it is just how much timestamp you wanna cover. You wanna put that way, that will be better. So if I say timestamp 10, there will be let's say my timestamp is 2 here. Okay, so if I call 0, it will be 1, 2, 2, 3. Okay, if I call 1, it will be 2, 3, 3, 4. So that that recurrence of remembrance is there, and that is how you provide it here. And that is why we are subtracting the sequence length from the length of data. Okay, this is how you will construct a touch data set for RNNs and LSTM for a character level. Okay, or not just character level, any token level. Now let's create the model where we'll use these attributes or parameters where we'll get the model type. So what kind of model we want? LSTM, RNN, GRU, BiLSTM. Okay, and then we have embeddings, and we'll provide the RNN modules as well, which will be there, and then feed forward. So these are there as attributes, and the arguments which we'll provide is vocab size, like what is the vocabulary size. That is what is going to determine your embedding, along with the embedding dimension. Like what happens is, let's say my vocab size is 50 and my embedding dimension is 512. Each of those vocabulary tokens will be represented in 512 dimension vectors. That is what will happen in N100 embedding, and this embedding will learn itself and update those vectors. Okay, and the hidden dimension, like I said, like what is the dimension of RNN and the number of layers and model type. So based on these, what we'll do is, if the vocab size and embedding dimension is provided, those will be instantiated with N100 and if the model type is RNN, we'll call RNN, LSTM, GRU, BiLSTM. What we'll do is bidirectional will be set to true. Okay, and if the bidirectional LSTM is set to true, the feed forward will become 2 times the hidden dimension and then vocab size. So feed forward is nothing but a dense. Okay, like I said, the dense is what will aggregate the information, right? So it will aggregate all those hidden states, and then it will multiply based on the vocab size to say this is the next token. Okay, so if it is not BiLSTM and it is normal models, the hidden dimension will be the same one. Okay, so now the forward pass, what happens is, first you'll compute the embeddings, and that will be provided to your RNN. So that will provide your output and hidden state. Okay, so you will provide this output alone to the feed forward network, and then you'll get the output, but you will return the hidden state because that is what will be used in your backpropagation and all. Okay, so the initialization of hidden states. The hidden states, when you want to initialize it, you'll initialize it as zeros. Okay, so you can initialize at zeros as it is provided here. Okay, you want to get the model, these are auxiliary functions, helper functions. To get the model, we'll call the text generation model with those parameters, and lot of things are provided in config class, and some are provided as parameters which are used here. Okay, vocab size and model type is provided as parameters, those are used here, and others are provided as config from config. Okay, when you call the train model, what we'll do is, first we'll import the loss function. So for you all who don't know the loss function, what is loss function? Loss function is the one which will say how much you are deviated to the current output. It is like the teacher putting you mark, but lesser the mark, better the performance. Let's say your teacher only puts negative marking. Okay, lesser the negative marking, better your performance, and based on those negative marking only, you will improve yourself, right? So that is your loss function. And the optimizer is Adam optimizer, which is the most famous optimizer. So before going through these, I'll recommend you all to have an idea on ANN optimizers and loss functions and all. Okay, so the optimizer is obtained, and when you call the model.train function, what happens is, for epoch and range of epochs, number of epochs you want to train yourself, we'll go through each of those data, and then we'll initialize the model, and we'll get the hidden state, okay, of the model. We are initializing it, right? Because you need something to start your time step. Okay, that is what is the initialization of hidden state. Because in case of RNN or LSTM or GRU, it is expected that you have a previous hidden state, and those previous hidden state at first time step is going to be 0. Okay, that is what we are doing here. Initially, the optimizer is set to 0 gradient, and that is provided to the model. Okay, the output or your your input and hidden are provided, and you get your output, which will become your input later, because that is what is there even in hidden state. Okay, and then you have your loss, which is calculated, And then you'll make your backpropagation based on the loss, and then you'll call the optimizer.step function. And then here it is just logging the loss at time step. Okay, so this is your training function. And the inference function, which is to generate, first we'll call the model.eval function to set it to eval mode, and then tokenize text, because once you get the text, you need to compute it as tokens, and you need to make the input tokens IDs, because there might be some tokens which will not be there in the vocabulary, and those you need to replace by UNK tokens. So that is what is happening here. And then you'll convert it as tensor, and you'll initialize the model hidden state, and you'll start your generation. This method is known as greedy decoding, where what we'll do is we'll call the model to generate the next token, and we'll see what is those token, and then we'll add it to the all the previous tokens. Okay, that is what happens here. The input sequence is there, and the next word IDX is there. Those will be added and then will be provided to the model again. This will be recurrent. Okay, the next best token will be calculated again. Okay, the next best token is obtained from here. So which will say across the 5,000 tokens, this is most likely to be the token. That is what is provided with this argmax, and that will provide your data text. Okay, so while you're creating your data set, first we are tokenizing the text. Okay, and once the tokenizing is completed, we are making a vocabulary based on calling the set. Set will basically remove your duplicates, and that will create your vocabulary. And then what we are doing is we are just providing index to word and word to index, so that you can map it forward and backward. And we are having a function to add UNK token. Okay, because it is not always possible that you will cover every tokens which you might see in the real world. For example, capital A and small a are different. Okay, so in those cases we need a UNK token. Those are added here. Finally, what we'll do is we'll convert those story which we tokenized as tensor. Okay, tokenized IDs. Okay, that is what will be there as data, and those will be provided to the story data set. And then DataLoader will combine this data set and make it as a batch, and then it will shuffle it and provide it to the model. Okay, that is what will happen with DataLoader. Then you'll call the train and save model, which will get the model, train the model, and save it. Okay, so this is basically the function which will integrate all of those other function. And then load model to load the model while you're inferencing it, because if there is a model which you trained already, you need not train it, right? So we'll load the model, which is text generation underscore, for example, if it is LSTM or GRU, whatever it is. So to inference, to run the inference, if you see, the generate text will have parameters like model start text from where you want to generate, word to index and index to word, basically your vocabularies mapping. Okay, so those all are provided, and finally your story is generated. So what we are doing here is, first we are preparing the data set. The story is already here. We are preparing the data set, and then the model type is here, LSTM. We are training and saving the model. The model is already there. If you want, you can comment this out, and then you can load the model again. But yeah, we are doing it at single time, so I've just commented it. So once you're starting the inference, we can start it as once upon a time, and then we'll run the inference where I need to generate 50 tokens after that. Okay, so let's do that. Python 2_ intermediate RNN nets story.py. So here, if you remember, we are training it for 25 epochs. Okay, so it will soon show here. Here you can see it is coming down. So yeah, here you can see once upon a time, there it is trying to say something, if I train it for even longer time, let's say 50 epochs, it will be even better. Okay, but this is how you'll make a story generator RNN. In the next section of prerequisites, we'll see about neural machine translation with the advanced section, where we'll see how to use encoder-decoder along with attention mechanism. That will be our next section. So yeah guys, I hope you all like this video. If you all like this video, please hit the like button, share it with your friends. If you haven't subscribed to the channel, please hit the subscribe button, hit the bell icon. I'll see you all in the next video. Until then, happy learning. Previously, we saw about the intermediate prerequisites, in which we covered about the introduction to deep learning. We saw in detail about Pytorch functionalities, how to use Pytorch dataset and DataLoader, what is neural network, how to create it from scratch. And then we saw a detailed working explanation on forward and backward propagation. We created a simple RNN network. Followed by that, we saw about the types of each components which are involved in deep learning training, which includes activation function, loss function, optimizer. And then followed by this, we also saw about RNN networks in detail, which includes RNN, LSTM, GRU, BiLSTM, with detailed working explanation, pros and cons, and then telling about how and why the model was created. So it was a pretty detailed video last time, and in this video we are gonna step up the prerequisite level a bit more, and then we are gonna start with encoder-decoder network. What is an encoder-decoder network? An encoder-decoder network is a type of neural network which is commonly used for sequence-to-sequence tasks like machine translation, text summarization, and question answering, where there will be a requirement for you to use a context. It has two main components, as the name suggests. It is encoder and decoder. Both components are typically RNNs, and in this explanation we'll use LSTM layers as the cells for encoder and decoder layers. Okay, encoder can be considered as a stack of layers, and for those stack of layers we are going to use LSTM layers. Okay, encoder and decoder network is not a neural network, it is a neural network architecture. Okay, please highlight the word architecture, because it will use any kind of layer which you'll use. So for example, you can use dense layers, you can use RNN layers, you can use even CNN layers. For example, if you have a task like let's say image captioning, then you can use CNN layers. Okay, all kind of these things can be done with the help of encoder-decoder network. Now, we already saw about LSTM that it is a type of RNN network which can handle long-range dependencies, and it will also mitigate vanishing gradient problem a bit, which was addressed as an issue of RNN. Now let's see, as usual, what, why, when, how about encoder-decoder network. Let's start with what is encoder-decoder network. An encoder-decoder network is a neural network that is designed to map an input sequence to output sequence. It consists of two main components, your encoder and your decoder. The encoder job is to process the input sequence and compress it into something known as context vector. It is a very important component, or in other words, we also call it as hidden state or thought vector, most commonly hidden state. Okay, we call it as encoder hidden state. Okay, now decoder will take this encoder hidden state or context vector, and then it will generate an output sequence. So this is how it will be like. You'll have your source, you'll compute embedding for your source. It will be provided to your recurrent neural network, whatever you have in your encoder. Now what you will do is, you have your targets. Again, you'll compute an embedding for that, and then this recurrent neural network information will be passed to this recurrent neural information, and final output will be provided out of a fully connected layer. Okay, so this is how basically any encoder-decoder architecture works. Okay, instead of recurrent, if you want to put it as CNN and then let's say ANN, anything can be done. Okay, but like I said, in this example we are seeing it with the help of recurrent neural networks, because usually encoder-decoder networks, in any one of these components, recurrent neural networks will be used, because if you use image, people use image in encoder only when it requires tasks like image captioning. So in decoder, anyway, you need to use a recurrent neural network. All right, so In this case, we are using LSTMs for both encoder and decoder. That is fine. Why should you use encoder-decoder networks? The encoder-decoder networks are basically suited for tasks where the input and output lengths differ, where order and temporal dependencies matter. I think this would be the perfect explanation about why you should use an encoder-decoder network. You see, let's take an example of translation. Okay, the input and output length will never be same. Let's say I'm translating a sequence from English to German. Okay, can you be sure that like if it is 5 words in English, it will be 5 words in German? No. And the order. So if I say I am making a course on LLMs, will that be the same direct word being translated in German? No, the order will differ because each language has its own syntax and semantics. That's why I said, in first prerequisites video, I told you that syntax and semantics play an important role. So here is a sample of that. So the order and the temporal dependencies also matter. Okay, so that is where you will use encoder-decoder networks. So some of the tasks are machine translation, text summarization, and then speech recognition. Why you have speech recognition? The input, which is audio frames, will have different length than the output text. LSTMs are used because they can efficiently handle sequences, especially with those long-term dependencies. The gating mechanisms inside LSTM will help you to retain or forget information over a long period, which is useful for accurately translating or summarizing sequences, which we know right now. Okay, when you should use decoder networks? By the understanding of why use decoder networks, you can crack it up a bit with when you should use. When you have variable length for input and output, when the task require you to understand the context and temporal dependencies inside an input sequence, and when you want the output to be generated step by step based on a previous output, then also you can use encoder-decoder networks. Okay, so this is when you should use encoder-decoder networks. Now let's see how an encoder-decoder network work. So let's say I'm converting it from English to French. So let's say the example is they are watching full stop and end of sequence. End of sequence means my sequence is completed. When I give it to decoder, what will happen is first BOS token, which is beginning of sequence token, will be provided. That is what is done here, like the embedding. First you'll embed your BOS token and that will be sent along with this information. Here you can see this information is passed at every state. Okay, and that is saying something like ILS. Now what you'll do is you'll together provide BOS and ILS, and that is saying regardant, and then it is saying full stop. Okay, here itself you can see there is variable length. They are watching full stop, but it is ILS regardant full stop. Okay, so this itself shows why you should use an encoder-decoder network for translation. Now let's see how it works mathematically and as an intuition way for encoder, decoder and all, and how you'll train that. Okay, so for an encoder, the input will be a sequence of words or tokens in English. So for example, it is I am learning deep learning. When you are processing it, each word will be embedded. Each word or token will be embedded into a vector by using vector word embeddings. Either you can use your word-to-vec, GLOW kind of pre-trained word embeddings, or if you think those are not enough, then you can use something like a custom NN.embedding layer. That is also possible. You can use that as well. Okay, so the LSTMs here keep an internal memory. So yeah, the sequence of word embeddings, again, I missed that point. The sequence of word embeddings is fed into the LSTM encoder, which processes the sequence at one time step at a time. Okay, one time step. So what does it mean? When I provide the word embeddings, each of these are going to be considered a time step. I am learning deep learning. So what LSTM encoder will do is it will process each of these one at a time, and then it will keep an internal memory of the previous words by using its cell state and hidden state. As we all know that it has those forget input and output gate, which will decide whether, like what information it want to keep and what information it want to discard. At the last time step, the word learning, the encoder will, when you process the encoder word learning, the encoder outputs a context vector, which is a compressed representation of the entire input sequence. Okay, so when you process this, you will have a representation, again, that is known as context vector or hidden state. That is a representation of this whole sequence I am learning deep learning. This context vector contains the LSTM's hidden state and cell state at the final time step. So if you process the entire sequence, it means it has seen the entire sequence and now it has the knowledge of this entire sequence. Okay, so that is why the final step, what embedding you get out of the LSTMs at the last time step, it will be a compressed representation of the entire input sequence. Mathematically, how it works is, for an input sequence, you will compute the hidden state and cell state at each time step, HTCT, where you will provide XT with the last, previous hidden state and cell state. The final context vector will be H_T, and that will be provided to the decoder. Okay, that is how mathematically it is done. In decoder, what happens is, you will provide a start of sequence token or beginning BOS token, both are fine. While processing, the decoder will use another LSTM network that will generate the output sequence one word at a time. Now we are considering in this example that you are using word level tokenization. Okay, so that is why it is said as word. The decoder is another LSTM network that generates one output word at a time. So at each time step, what you will do is you will take the previous word embedding and the context vector, and that will be provided as input, like I said here. So if I say it is BOS, it is saying IELTS. BOS and IELTS will be provided together, and then that will say regarding. That is what they are trying to say here. Okay, it outputs a predicted word, and this word is again fed back for the decoder for the next time step. This will continue until the decoder generates a token known as EOS, which is end of sequence token. Here it means that it is end of translation. For each time step, there will be an output here, H-T and C-T. Here, Y of T-1 is the previous word. YT-1 is the previous word. Let's say if you are starting with SOS, okay? And H-T-1 and C-T-1 is the previous hidden state and cell state of the decoder. While you train the encoder-decoder network, you will train it both together. Backpropagation also will happen together by using a loss known as cost entropy loss, which we saw previously already. The model will learn to predict the correct sequence of output given the input sequence. Since we use LSTM, the backpropagation will be backpropagation through time. If you see an example, here I'm saying I'm learning deep learning. It is Jesus apprendre le apprentice. I'm sorry for my French, but there is a sample here. Okay. In encoder, what happens is, for each of these token, there is an embedding being computed. All of these are provided one by one to the LSTM cells in the encoder, which will provide a hidden state and cell state for each word. Finally, context vector is obtained after processing all of these words, which will look something like this. Okay, and the decoder time, step by step, what happens is, first time step, SOS is provided, which will predict the word ja. And then in the next time step, you'll provide the ja along with the context vector, which is here already, and it is saying SUS, and this process will be repeated until EOS token is predicted. This is how an encoder-decoder works. So as a summary, you can say encoder-decoder is a network which is designed for sequence-based tasks where input and output lengths differ, and here we have used LSTM to maintain long-term dependencies. The encoder's work is to compress input into a context vector, and decoder's work is to generate an output sequence word by word or token by token based on the context vector. So the main thing is, this architecture is highly flexible and can be adapted to various applications like machine translation, image captioning, speech recognition, and so on and so forth. Now that we know theoretically on how an encoder-decoder network works, let's create an encoder-decoder network for translation. Here I have a Jupyter notebook. Again, we are not going to train it with that. We'll train with the script. But in Encoder-Decoder notebook, we are going to step this up a bit by adding a simple component, but which has tremendous upside to it, which is attention. We'll see about that. Okay. So first, we are going to use sequence to sequence model that we know. This is a model which will convert an input sequence to an output sequence of variable length and has some temporal dependencies in it. So for these, we'll use Encoder-Decoder. For attention, we are going to use a mechanism known as Bahdanau attention, which allows the decoder to focus on different parts of the input sequence at each time step, which will improve the model's ability to handle long sequences and complex relationships. Okay, so what does this mean? See, I have an input sequence here. I am learning deep learning. Okay, if I don't provide an attention mechanism, each word will be provided equal importance. Okay, but when you add an attention, it will process these sequences of different parts in different ways. Okay, so that is what is attention mechanism. So for example, a lot of importance will be given to words like learning and deep learning. Okay, because those are very important here. Am is not at all important. I would have been more important than am, like that. Okay, so what are these attention neural networks? Attention neural networks are neural networks which incorporate attention mechanisms to dynamically weigh the importance of different input elements while generating each output element. For example, if I want to generate an translation, right? If I want to translate output of, let's say, deep learning, I need to focus more on deep learning rather than, I am and all. Okay, so that will help you a lot. That's why we are going to add a component known as Bahdanau attention. We know about the encoder-decoder model, but here we are adding an attention to it. Okay, so let's see how the model will look like. This is how an encoder is. Like, it sounded very big, right? I'm not sure how it sounded for you. It sounded pretty big for me when I was learning it for the first time. But it is very simple. All you need is an embedding layer, and then an LSTM layer, and then a dropout. Dropout, like I said, is for regularization. So what you will do is, first you'll compute the embeddings for the tokens. You will apply dropout for regularization. You'll provide it to your LSTM and then get your output hidden and cell state. And that is all you do in encoder. If you print your encoder, let's say my input dimension is 10, embedding dimension is 512, hidden dimension is 1024, num layers is 5, and then dropout is 0.0, let's say 0.1. Okay, so if this is my encoder network configuration, this is how it will look like. Okay, so LSTM will have 5 layers. 5 layers of LSTM, it will go through all of those. Okay, so this is how my encoder will look like. So the explanation is that it uses an embedding layer to convert input tokens into dense vectors, and then it will use a multi-layer LSTM based on the number of layers we provide. And then the forward method returns the following outputs, which will contain the hidden state for each input token, which will be useful for attention computation. The final hidden state of the LSTM, which is your context vector, along with the cell state. Okay. Now, Bahdanau attention mechanism. Bahdanau attention mechanism is a key innovation that allows the decoder to focus on different parts of the input sequence at each decoding step. How will it look like? Okay, how the architecture will look like when you use an attention to it. That we are going to see now. Without Bahdanau attention, this is how it will look like. You'll provide the source to your encoder by computing the embedding. It will create all the recurrent neural network, and those state will be provided to the target. That is how it works, right? But here with Bahdanau attention, what happens is you'll get your recurrent information, and that will be provided to something known as attention. Okay, and those information are still provided to recurrent neural network. In the target side also, the attention will be, the information will be added to the attention. So this attention will aggregate all those information and say like, this is where you need to focus for your next output. So that is why there is a self connection here. Okay, this is how a Bahdanau attention mechanism works. So Bahdanau attention mechanism is nothing a lot of like complication and all. It is just gonna be a linear layer, and then you'll use tan function because that will say that intensity of how much you need to focus. If you remember about the memory gate, you'll know that tan is very good for these kind of situations, because it says like where you need to like how much you need to focus, like that, right? So the attention goes on like this. The attention layer is nothing but a linear layer here, with dimension being hidden dimension cross 2 comma hidden dimension. Why? The attention will be computed on both hidden states and encoder output. Hidden state is nothing but your context vector. So along with that, you'll use your encoder outputs for your attention, because hidden state is a compressed information, while encoder output will have like the overall information about the encoder sequence. Both are almost similar. Okay, so what happens is you will first take the hidden state and encoder output and format it in such a way that both of these are having the same shape. That is what has happened here. And what we'll do here is we'll concatenate those two together. Okay, at dimension 2. Dimension 2 is nothing but your embedding dimension. At embedding dimension, these will be concatenated together, and then you will perform an attention mechanism, after which you will call a tan function, which will say, okay, this is where you need to focus. Okay, this is how the attention is. And then what you will do is you will provide it to another linear layer, which is self.v, which has a dimension of hidden dimension comma 1. So it will say like this is the token you need to process. Okay, this is the information you need to process on. That is what is hidden dimension cross 1. So now what it will do is, now you will apply a softmax function which will classify and say like this is basically how you need to focus, because it is like your flattening which will happen here. And then what you will do is once you compute the softmax, it will say the probability for each token where you need to like how much you need to attend on. That is what is in the explanation here. It calculates an energy score where you will first concatenate decoder hidden state with encoder output. It is a decoder's hidden state. Okay, and then what you will do is the concatenate vector. Why it is decoder hidden state? Here you can see this is being provided from here, right? It is decoder hidden state. This concatenate vector now will be passed through a linear layer, which is self.attention and the tan activation function. That is what is here. Okay, so what this another linear layer will do is that there will be another linear layer. It will reduce this to a single score. This will be across dimension, but it will reduce to a single score because you have a single sequence, right? This energy score again will be converted into probabilities using softmax, and these weights will determine on which part you need to focus on in the input sequence so that you can generate the next output word correctly. Okay, this is how the attention mechanism works. All right, now let's see about the decoder. The decoder will take an embedding, an LSTM, a final linear layer output, and then you have a dropout. Okay, so first you'll get the input, you'll compute the embeddings, and then you'll apply a dropout. And then what you will do is, right now for the first time step alone, you'll take the hidden of -1, which is HT -1, and that information is your beginning of sequence token. Okay, and then along with the beginning of sequence token, you will provide your encoder outputs, which is your context vector, together. Here you can see the self.attention is attention being provided, and that attention is nothing but a Bahdanau attention. Okay, so once you provide that, you will have your attention related information, and that information will be multiplied. That is what is BMM, batch multiplication, batch matrix multiplication with the encoder outputs. Okay, in the encoder outputs, you will multiply the attention information, and that will say like this is where you need to give the importance. This token is very important because the token information is there in the encoder output, and where you need to focus on is there in the attention related information. So if you multiply both of these, you are going to give a weighted information on, say, like, this token, you need to focus this much. So that is what is obtained from here. And now this becomes your RNN input. And once you provide this, you will get an output hidden and cell state, and that will be provided to your fully connected layer, finally providing a token. Okay, so we'll also provide this hidden and cell state along with the predicted token, so that in the next time step it can be repeated, the process can be repeated. Okay, that is what is provided as an explanation here. And in as a whole, how the architecture works is, you will first initially have everything as zeros. Okay, as far as outputs is concerned, because you need to fill there. First you'll get the encoder outputs, and then what you'll do is you'll go through the length, max length you have, and what you'll do is you'll provide each, the output and hidden state being combined to the decoder, which will provide an output itself. And then what you will do is you'll use a method known as teacher forcing. Okay, teacher forcing is a method where what happens is, let's say your token is the task is to convert English to Tamil. Okay, and it says I love AI. Okay, and it translates in Tamil as எனக்கு AI பிடிக்கும். So when the translation happens while training, if it says I as nan is also a word to say about I in Tamil. When you are using teacher forcing, what you'll do is, instead of using nan, you'll replace it with எனக்கு. Okay, so that is what happens with teacher forcing. It is, you will force your model to generate the correct token by providing it with information which is there in the ground truth. The information which is there in the ground truth becomes your teacher. That is what is teacher forcing. So what we are doing is, the ratio is 0.5. So whenever there is a possibility of 0.5, what you will do is you will replace the most recent token with the correct token at that time. Okay, so that is what is teacher forcing, and that mechanism is used here. So here you can see it is usually used for training stability. Okay, so how the training loop will be, we'll use the multi 30k dataset of German to English translation. We'll first build the vocabulary for both languages, and then we'll create data loaders for batching and training. A model architecture is implemented, which we already saw here. We'll define the training and evaluation loops. We'll use Adam optimizer and cross entropy loss for this. We'll also implement teacher forcing during training, and this is a strategy for training recurrent neural networks where you'll use ground truth as an input instead of model output from a prior time step as an input, so that it is more stable and learns a lot more. For evaluation, you'll use a method known as blue score, and this blue score is very famous for evaluating machine translation task, for comparing it to human translation, where what it will do is it will check for word and phrase matches. So the range at which this happens is, it is between 0 to 1, with higher being better score. Okay, this provides functions for you to translate individual sentences, and finally we'll calculate blue score on test set. Okay, so this is how the flow is, and now let's see how that happens. Okay, so here we have the training code. I'm not going to speak about the model architecture and all. Okay, I already trained it because it took some time. Okay, so I already trained it. We'll infer it though. Okay, so here you can see we have set some loggings here. Seed is set. So this is how the data set is constructed. We'll get the source file and target file, which is nothing but the txt files of German and English. And then what are all the transformations you need to do on the source sentence and target sentence, which is there here. Okay, so what we'll do here, first we have an auxiliary function known as load data, which will load the file based on the file path. Okay, so it will read lines, which means you'll have a list of data. Now this self.source data will become the length, and will call the data at that index, will transform it, and then will provide the output, okay, as source and target. For tokenization and all, we are going to use Spacey. So Spacey is a library which has a lot of NLP functionalities in it. One of those is pre-trained tokenizers, and we are going to use that for Spacey D for German tokenization, and Spacey EN for English tokenization, which is your target. And the vocabulary is decode news SM, which is something you need to install. Okay, so first for that, what you need to do is Python-m Spacey download decode news SM. You need to do this along with ENCore web SM. Okay, here we have two helper functions, which is tokenize D and tokenize EN, where what happens here is with tokenize D, first you will normalize your token by computing it to a lowercase, and then you'll tokenize it with the tokenizer appropriate to the language. Now, here are the training paths. I've already provided all of those here with the resource folder. You'll have all of these files in your resource folder, so you need not worry. What we are doing is we are creating instances for the multi 30K data set for each data, training data, validation data, and test data. So what you need to do is just provide the file path along with the tokenization transformation path. Tokenizer. Okay, so basically what it will do is it will tokenize the sentence and provide the tokens for source and target. That is what will happen with the data set. Okay, so now we need to create the vocabulary as well. Here we have the part token, start of sequence token, end of sequence token, and UNK token. This is unknown token. Unknown token is used when there is an occurrence of a token which the model hasn't seen before. That is what is unknown token. So create vocabulary is used, and that is nothing but you'll just take set. If you call the set on the vocabulary, what it will happen is it will give the unique words. That will be a vocabulary. Okay, that can also be done better like this. Okay, so now what we are going to do is we are going to tokenize all the sentences which are there in the training data. So that is done here. Train D tokenized, train EN tokenized, and then we have computed vocabularies for that. Now you have source vocabulary, target vocabulary, tokenized training data set. Here we have defined the model architecture, which is already there. And what you need to do is you need to provide these model hyperparameters. I have set it for 256 embedding dimension, 512 hidden dimension. Hidden dimension is the dimension with which your feed-forward network works. And I've just used 2 layers. You can use more. That is your wish. And encoder-decoder dropout probabilities have kept it pretty high so that it doesn't overfit. Okay. So this is how the model is created now. Now I'm creating an optimizer of Adam by providing the model parameters. I haven't provided a learning rate. By default, I'm just leaving it to be default, and the default learning rate is 1e minus 3, okay, 0.001. And then for loss, I'm using cross entropy loss, and what we're doing is we'll ignore the padding index, and padding index is the index of pad token. Okay, so collect function is the function which will create the batch. Okay, so that is what happens in the collect function. So what here we will do is we'll replace the tokens which are to be padded. Okay, so for example, my sequence length is 512 and I have only, let's say, 200. So the next 312 sequence 12 tokens will basically be padded with the pad token. Okay, so that is what pad sequence is. Pad sequence is a function which will by default do that, and that function is from utils. Okay, so that will provide you your source and target batch which is ready for training. And in training loop, what happens is you'll set the model to training, your epoch loss will be set at first as 0. You'll go through the source and target values in the data loader. I've just provided TQDM so that you will have logs and then you can monitor what is going on. You'll first set optimizer to 0 gradient, and then the model will be provided with the input. It will provide an output, and then what you will do is you will take your target, which is your label. You will compute loss with that. You will call the backward propagation, and that will be ready for backward propagation. Your clip grad norm is done so that it doesn't fall into exploding gradient. Okay, it doesn't fall into exploding gradient. And then what you will do is you will call the optimizer.step function so that the weights get updated, and then we are just adding those loss so that we can print the loss. Okay, in eval what you will do is you'll go through the values again, and then again this process will be same repeated, but the data loader would be eval data loader rather than the train. And here you won't use those optimizer or criterion because those are not required here. Okay, but still loss calculation, those are going to be the same. This is very important. This is translate sentence. Okay, translate sentence is the function which we will use to translate the sequence which is in German to English. So tokenize DE, first what it will do is it will tokenize your sentence which you provide, and then it will add the start of sequence and end of sequence token. Okay, so you are getting the indices of those tokens. So what you will do is you will create the tensor. The source indices can be set as the input IDs. Okay, these input IDs are provided to the encoder, which will provide your encoder output, hidden state and cell state. Again, as you all might know, we'll provide those to decoder along with the start of sequence token. Okay, so that is what here it is. Okay, target vocab of start of sequence token. We'll take the start of sequence token, will compute a tensor for that, and that will provide the start of sequence token ID as target tensor to start with. And then you're providing a hidden state, cell state and encoder output, and that will provide an output, hidden and cell state. Now what you will do is you'll see which token is the most probable token with the help of argmax, and then that token will be appended to the target indices. And again this process will be repeated unless and until you see a token which is EOS token. Okay, so finally we'll decode those tokens by calling the indices on the vocab dictionary we created. Okay, we'll ignore the SOS token and US token, and then finally your tokens are provided. Okay, so I've commented the training loop here. I've created the data loader, train data loader, val data loader and test data loader. I've commented the training loop because I just wanted to show you the inference. Training is done, but still, yeah, you can also do training by just uncommenting these. Okay, right now loading the state dict. State dict will load the weights. So I have the weights stored as bestmodel.pt, which is saved with the help of torch.save function. Okay, so you can see model.stateDict is saved as bestmodel.pt, which is already available here, and I'm loading that into the model. Now the weights are loaded, which means you're like, it is like if you've seen the Matrix movie, they'll insert a CD which will load all the information to the brain of the user. Okay, so that is how like load static basically works. Okay, and now what we are doing is we are taking 3 samples from the test data, and then we are calling the translate sentence function. Okay, let's see how the model translates. So now if you see, it will just try to load this state dict into the model, and then it will try to translate the sentence. Okay, so here you can see there is some value here, and the target is 2 young white males are outside near the bushes, young men outside near their seats, something like that. Okay, so this is not an accurate one again, but we can train it for a longer time. That is there. You can adapt the parameters. Probably that could be your exercise. Compute the blue score. I'll probably make a leaderboard. Let's say we'll take 1 week from now. Okay, and let's see who gets the best model. Okay, let's keep that as a challenge of neural hacks with Vasanth challenge. Okay, so here you can see a group of men wearing hard hats, something like that. So here is men hard hats, those are there. A little girl climbing into a wooden playhouse. A little girl is into a small of a wooden playhouse. So it is trying to, like recognize the entities correctly, but the grammar is not that good. You need to learn that. If you increase the layers and hyperparameters being tuned, that will happen. Okay. So yeah, guys, now you have reached the end of the prerequisites. From next video, we'll be moving into the course, starting on with the explanation on the paper. Attention is all you need. I'll see you all in the next video. Until then, happy learning. If you have any thoughts you want to let me know, please let me know in the comment section. I'm very active in that. Please let me know your like or dislike with the help of the buttons which are provided. If you haven't hit the subscribe button, please hit the subscribe button, and yeah, share it with your friends as well. I'll see you all in the next video. Until then, happy learning.